Okay, so we are live. We're very happy to have Matthew Heydeman, who will be telling us about black hole, BPS black holes in AD as 3 times S, 3 times S, 3 times S1, and beyond.
Okay, great. So yeah, first off, I'd like to thank the organizers for giving me the chance to speak. Obviously, it's always more fun to come to Paris than to do the Zoom talk, but this is good. And I'm talking about a paper that we just put out a couple of weeks ago. So it's hot off the presses, and I think it's this topic is very well suited for this audience because I know that several people are working on at least some somewhat related backgrounds that I'm going to be describing. So most of what I'll be presenting today is work with Joaquin Toriachi and his graduate student Xiaoyi Shi, who's a great student that did some crucial calculations in this later part of the paper. Um, so as the title says, I'm going to be talking about BPS black holes and ADS3 cross S3 cross S3 cross S and beyond. But actually, the beyond will be coming first. So I'm going to say a little bit about the beyond, and then the latter half of the talk will be focused on this background. So I couldn't give a whole talk that was just super technical about this background. I want to give a lot of motivation first to explain why the results are sort of reasonable and why they are surprising. So that's part of the logic. A secondary point that I'm going to make about this talk is that it does tend to run over time. I tried to shorten it down, but I know that at this conference in particular, people tend to ask a lot of questions. It's very likely that it'll go over time, and I really apologize. I don't want to cut in anyone else's time, but we'll see how many questions there are, and I may have to rush a little bit towards the end, but hopefully people get the main idea. Okay, so what is the plan today? The plan is the very first thing, which I'll spend a lot of time reviewing, is how we can understand near extremal black holes and how can we understand them quantum mechanically. Then once I've explained a little bit about this near extremal and what some of my previous works are that helped understand the quantum mechanical part of this, then I'll discuss in detail some spectrum of BPS black holes with small n equals 4 supersymmetry. So ultimately, this near extremal limit is going to be tied to the so-called Schwarzian theory, and I'll review a little bit about this Schwarzian theory with 4 supercharges, which we constructed several years ago and solved, and it makes nice predictions for instance, the D1, D5 CFT that people are very familiar with. Now, after talking about small n equals 4 supersymmetry, then I'm going to ask, can we generalize our construction? So can we, in some sense, classify supersymmetric black holes and put constraints on what kinds of supersymmetries they can have using the above technology? And then only then, so this was all the beyond, only after I say all these things, then I will finally come to the BPS black holes and ADS3 crystals swollen, which sort of appears as an exceptional case of our classification. And this will have a lot of wacky predictions for the BPS spectrum that it would be nice to understand microscopically. So most of what I'll be talking about is supergravity and supergravity near the throat. That will be the key player throughout this talk, but some of the predictions are things that can in principle be computed in the dual CFT. So that's the overview. Now I'm going to rush through some of the review a little bit. Okay, so the main thing when we're talking about black holes in, let's say, Euclidean signature would be that we write down some solution to the Einstein equations like Schwarzschild here. Here I've written as a function of m, but you can also write as a function of the inverse temperature. And the idea, of course, is that in Euclidean signature, if we sort of draw this metric, it will look like a cigar. So I'm suppressing, this is in 4D, for instance, now. So I'm suppressing these angular directions and just drawing the RT plane. The idea being that in Euclidean signature, the metric asymptotes to far away to flat space, but with a time direction that's periodic, right? So this is Euclidean thermodynamics, is that the thermal circle in Euclidean time, which will have length beta, which is the inverse temperature. This is some kind of boundary condition that we fix at infinity. So we fix some potentials at infinity, like beta and other chemical potentials. And then the idea is that this particular metric, when drawn, will look like a cigar, and the horizon sits at the tip of the cigar. So, maybe this picture is only approximation of what's happening in string theory, but the idea is that this is sort of the leading order way to get the black hole entropy. This is the slickest way of doing it, is to basically write the thermal partition function as a function of the boundary conditions that we fixed. We'll approximate it by e to the I classical, where I classical is the Einstein-Hilbert action associated to this solution. And when you just do this, the miracle is that you can, as Gibbons Hawking point out, the miracle is that you can interpret I classical as a thermodynamic free energy. So, why we're allowed to do that is sort of from this Euclidean point of view, that's sort of part of the mystery of black hole thermodynamics, is why does the classical action in particular have a temperature independent piece that has all the properties of an entropy? And of course, when you actually compute what S is, it's A over 4G, which is the Hawking result. Okay, so this is the old story, and of course this story works pretty well, but we know it's not an exact description, right? We can get things to be a little bit more interesting, for instance, if we want to, we might want to understand black holes as quantum mechanical systems and compute their partition function, right? So in some approximation, compute the partition function of some quantum mechanical system. That's what we might want to do. And one of the first things that we like about quantum mechanical systems is like we like to study the ground states or the low-lying energy levels of the quantum system. So for energy, for low-lying energy levels, that's roughly speaking when this energy is taken to be very small. But of course, for Schwarzschild, if you take the energy or the mass to be very small, then the geometry will become singular, and maybe this path integral approximation is not good. So we can do a little bit better if we want to focus on ground states is by adding electric charge. And that will essentially lower the Hawking temperature. So in the Reister-Nordstrom example, when we add some electric charge Q, the cigar gets longer and longer, and the thermal circle direction gets longer and longer. So the temperature is the difference between M and Q, with Q being what will end up being a BPS bound in, let's say, 4 dimensions. But for now, it's just an extremal bound. So a black hole, when you truly saturate this, has 0 temperature, and the entropy can be written as a simple function of its charges. And the idea is that we want to understand the path integral near 0 temperature. In this kind of example, ultimately we'll be doing a much crazier example with many more charges, but the same principle applies, so that's why I'm reviewing this now. So this idea where we compute the partition function by saddle point, that's sort of a one Euclidean way of getting to Hawking's entropy formula, right? And Hawking's formula for the temperature. But the problem is that when we consider this solution, we had this idea that a black hole whose mass and charge are very, very close, it has a very low internal energy. Roughly speaking, the energy is the difference between these two quantities. And so, and also the temperature will be low. Depending on which ensemble I use, it'll either be the energy in the microcanonical or the temperature in the canonical. So let's think about things in the canonical as we lower the temperature to 0. So one of the things that was pointed out all the way back in 1991, which is called Limitation Statistical Description of Black Holes from Preskel, Schwarz, Shapir, Trivedi, and Wilczek. So they argue that the description of a black hole as a statistical thermal object must break down as the extreme 0 temperature limit is approached due to uncontrollable thermodynamic fluctuations. So what's the argument in this paper? Well, you can, roughly speaking, you can compute the variance of some statistical mechanical quantity, and if the variance is bigger than the expectation value, then this equilibrium is not obeyed. If fluctuations are bigger than the equilibrium value, then the thermodynamic equilibrium is not obtained. And the argument of, roughly speaking, is that as you lower the internal energy of the black hole, let's say this charged black hole example, the idea is that there'll be some ground state energy, which means we can sort of subtract off, and then the correction above the ground state energy is, in the grand canonical ensemble, proportional to t squared. But if you use Hawking's calculation from which you derive the temperature from this, Hawking quanta point of view, this Lorentzian calculation, you would find that the average energy of a Hawking quanta is linear in t. So of course, for large temperatures, the energy that the black hole has goes like t squared, and that's a lot bigger than t, right? So a single Hawking quanta carries off about this much energy, but the black hole has a large amount. But of course, right around this M gap scale, which is just a number that you compute from the geometry, it's the heat capacity of the black hole, and they wrote it here in some different language in this paper. When you get down to this M gap scale, actually, the Hawking quanta carries more energy above the ground state than the black hole itself. And so this is related to the fact that there are uncontrollable thermodynamic fluctuations, and the black hole has insufficient mass to emit a single Hawking quanta. So if you just use the Hawking answer, it looks like for let's say the density of states. So the density of states will be the Fourier transform of the partition function. So this is the microcanonical density of states. And so Hawking's formula is totally fine and works up here and agrees with is reproduced by the extremal Reister-Nordstrom answer. But as I lower the energy of the black hole, or equivalently as I lower the mass, closer and closer to mass equals charge, right around this M gap scale, the claim is that Hawking's proposal is supposed to fail. Of course, if we could extrapolate all the way down to 0, we would get some e to the extremal entropy, and that's the business of supersymmetric black hole microstate counting is supposed to count these guys, but the problem is that the gap scale enters sooner. So this thermodynamic fluctuation problem is a problem in this region for low energy black holes, or black holes at low temperature. So how do you resolve this issue with the thermodynamic fluctuations? Well, the issue was that we use the semi-classical approximation, but we really should be doing a true quantum mechanical calculation, which of course in quantum gravity in general you can't do. It might not even make sense, but we can at least improve the Gibbons-Hawking procedure exactly in the place where the calculation breaks down. So that's the overarching idea. So to actually make this precise, to turn that sort of doing quantum mechanics in the throat region, to make this a little bit more precise, we have to just draw some pictures. So, well, I guess pictures are not usually precise, but there's a calculation behind the pictures, which isn't what I'm trying to describe. So the first crucial ingredient is that, let's say in this 4D example, far away, the black hole looks like flat space, but as we approach the horizon of the black hole, if we have a black hole very close to extremality, we have a very long throat region. Now, if we could take the black hole all the way to extremality and then go zoom in on the near horizon region, we get this ADS2 cross S2 geometry. But sort of there was very long-standing puzzles in trying to make sense of ADS2 cross S2 in terms of more familiar things like ADS5 cross S5. I mean, the basic idea is that you could find an ADS2 cross S2 solution and it's supersymmetric and it has a non-vanishing entropy from this path integral point of view, but certain quantities kind of diverge. You have some 0 over 0 kind of issues. And if you also try to put finite energy excitations in this space, it will mess up the ADS boundary conditions. So that's why people will say that some people will say that there's no real example of ADS2 CFT1. CFT1, of course, already has to be a little bit strange.
But that's bonkers because you can build solutions asymptotically ADS2, which are due to CFT1 states, and you can build lots of solutions. So of course there's an ADS2 CFT1. It's just not ADS2 CFT1 does not have a conformally invariant ground state, but there is an ADS2 CFT1 correspondence. There are many solutions. There are many CFT1 states. It's just if you look at the wrong ADS2 vacuum, which preserves conformally invariant, of course you don't get any excitation. But if you look at vacua which break conformally invariance in the infrared, of which you have lots, then it's okay. It's like ADS3. ADS3 Poincaré does not have, I mean, the ground state, the Ramon ground state naive solution it doesn't have any excitations, but it's not in the spectrum. The Poincaré, the ADS3 Poincaré also you have ground states which break conformal invariance. So I don't know who is saying ADS2 CFT1 is not correct, but it's clearly bonkers. I mean, I don't know.
All
Maybe
right.
later, but I don't think anybody serious should say that.
Okay, let me not try to paraphrase what people say. It just, obviously, if you had a CFT1, the stress tensor would have to vanish, right? So you need to break conformal symmetry in some way or another to get something interesting.
Indeed.
Yeah, okay, I think we're in agreement on that point. And indeed, I'll be breaking conformal symmetry by some soft mode, as you know when this is coming. But for people who are not familiar, conformal symmetry is going to get broken very soon, first in 2 dimensions, and then embedding into the higher dimensional problem. So we're going to break conformal symmetry. So the breaking of conformal symmetry and sort of this back reaction argument was discussed in a large number of papers, starting essentially with Kitaev's discovery of some kind of model that's related to ADS2 gravity. So the idea will be that in the throat region, we can break conformal symmetry by a little bit. So turning on finite temperature breaks the conformal symmetry. If we have 0 temperature, then the proper length of this ADS boundary is infinite. But if we have finite temperature, so imagine this is the cigar that we smushed onto the plane, and it roughly speaking has a hyperbolic metric, right? So the idea is that for finite temperature, we would fix the length of the boundary curve, and then we are supposed to integrate over all metrics that have the same length. That's sort of the path integral point of view. So before, we approximated that path integral by saddle point, and the saddle point is the empty ADS2 solution. But if we turn on small finite temperature, we actually have to correct the saddle. And we should do even better, which is that we should also evaluate one-loop fluctuations around the saddle. And one-loop fluctuations, if you look at the set of boundary conditions in some particular dilaton gravity theory, which is JT gravity, which was what Kitaev studied, and then a lot of this was explained by Olmeri and Polchinski, and then the most clear example where this picture is taken from is Maldacena Stanford Yang. So there's some 2-dimensional dilaton gravity, which again, this is just a toy model right now. So there exists a 2-dimensional dilaton gravity, which has an ADS2 vacuum, but you can also compute one-loop fluctuations around the vacuum. And you can interpret those one-loop fluctuations in this JT gravity model. The idea is that it's not pure Einstein gravity, that there's an extra scalar field whose equation of motion forces the geometry to be ADS2 locally. So this is what this phi equation of motion does. It sets r equals -2. But it turns out that if we choose boundary conditions for this gravity theory, in which we fix the temperature, we fix the length of the boundary, we can have different kinds of geometries, which are still locally ADS2 everywhere, but differ in the choice of the curve that we choose. A sort of think of Pfefferman-Graham, essentially, right? So we could foliate this ADS2 by slices, and there's sort of different geometries of the slice, which correspond to, they have the same integrated boundary conditions, but locally they fluctuate. And so these local fluctuations, they only show up at finite temperature, and they enter through the Gibbons-Hawking-York term. Okay, so this was a lot to say. It's just, for now, and all these authors essentially studied a simple model of dilettante gravity where there are non-trivial finite energy excitations, but they're pure boundary excitations. This is very similar to 3D Chern-Simons gravity. So for me, this is a nice toy model, but we ultimately want to do full higher dimensional black holes and string theory and all that. So we have to understand if this simple model can be useful for something in higher dimensions.
Matt, I have a question about higher dimensions.
Yes.
I mean, why do you have the right to fix the length of the boundary from the higher dimensional perspective?
We also do that here. This was true even on the first slide. We always, far away in the asymptotically flat region, in Euclidean signature, we have a compact Euclidean time direction, and I choose the length of that compact Euclidean time.
Yes,
that's the cigar picture here.
Yes,
there just should be an S2. Yeah.
Yes, this I agree, but the ADS2 is in the deep interior of the geometry.
Yes.
It's not asymptotically in the geometry in the context of the 4D solution, let's say.
Yeah, so I mean, the length of the time circle is something that we fix at infinity. Let's say we choose that we're going to fix the time circle at infinity, and then then we find a solution that has that boundary condition, and that solution might have a long ADS2 region. Yeah, of course. The idea is that I fix the 4D boundary conditions, and then I kind of RG flow into the two-dimensional region. And that's sort of the idea of why this cartoon dilettante gravity can say something about higher dimensions is that this is exactly an infrared effective field theory. That will be the statement. If you don't like it, don't worry. We'll get the black hole entropy and stuff correct later on. But for now, this was just a toy model. In the application of higher dimensions, this is supposed to be the infrared phase, that it tells you if I very, very, very slightly break conformal symmetry by turning on a temperature, it tells me what the low energy degrees of freedom are. It doesn't tell me that there's a UV 10-dimensional string theory or supergravity. It just says that there are very small metric fluctuations that have very low energy. And this is capturing those. Everything else has been integrated out, like quite literally integrated out, as we'll see in just a second. So the idea is that this 2D dilettante gravity, the bulk term is basically trivial. It's just a Lagrange multiplier. Well, it's not trivial, but it enforces a constraint, and all the action comes from the boundary. And if you plug in this sort of wiggly curve picture, choose a particular Pfefferman-Graham curve that satisfies the boundary conditions, plug it into the action, and evaluate the Gibbons-Hawking-York term, you find that the action, the boundary term here, reduces to the Schwarzian derivative of f of t, where f of t was sort of an arbitrary function that I chose. So the idea is that there is a family of different geometries with different cutout boundary conditions, and if I evaluate the action for that family of geometries, the action comes out to be the Schwarzian derivative of that function. You can just do this by plugging in, choosing an f of t and plugging into the action and evaluating the curvature. You see that it comes out to this crazy nonlinear derivative. So this is a nice function, and it's nice because, first of all, what it tells you is that if this function was just a pure SL2R transformation, so if this was a fractional linear transformation, then the Schwarzian annihilates it, which sort of makes sense because any two geometries that are related by an SL2R symmetry really have to be identified in the path integral. So this only counts geometries, by counts geometries, I mean this only weights geometries that are genuinely distinct metrics, not related by isometries. So you can make this look closer to 3D gravity by passing to the first order formulation. So you can introduce the field lines and the spin connection. And the spin connection, so I've now gone to these like horospherical coordinates or something like that. So e to the r, the metric grows like e to the r, But this Schwarzian term, in general, I could put a general function here, but this thing is this general function. When I ask what happens when I act with gauge transformations, it transforms like the Schwarzian derivative. So I've just put the Schwarzian derivative in at the start, but you can show that it has to be that. Now, in the first order formulation, in terms of the field bind and spin connection, the torsion's not automatically constrained. So the idea is that I can introduce Lagrange multipliers for the torsion and then assemble these field binds into some kind of spin connection or some kind of SL2R connection. And then the action of JT gravity becomes just a BF theory with a BF boundary term. So this is sort of the relation between 3D Chern-Simons gravity and JT gravity. You can write it as the BF theory. Oh, sorry, I already explained this. So the Schwarzian is really supposed to be an arbitrary function, but you act with bulk diffeomorphisms, which maintain the asymptotic form of the metric, which is explained in this Cousineau paper. If you play this game, you'll see that it has to be the Schwarzian derivative. And there's a natural boundary condition that you get from the 3D picture as well. Obviously, there was no 3D gravity here, but if you follow the same kinds of steps, you can treat JT gravity like a Chern-Simons theory. Okay. So this was just all some rewriting of a toy model. I explained how the toy model reduces to a boundary term. I explained how you can rewrite it in terms of somethsomething that looks kind of like a TQFT, kind of suggests that the theory could be solvable, even though it has a crazy, Schwarzian derivative in there. So what are we going to use this theory for, right? So back from the higher dimensional point of view, the first thing we did was just say that the path integral is e to the I classical plus potentially subleading geometry. So this is kind of the WKB approximation. But WKB really says that for any classical saddle, we should at least compute the one loop determinant. Now, there's a long industry of people computing, in particular led by Ashok Sen, of people computing the one loop determinants as a function of, let's say, the area of the black hole. So he chooses the ADS2 solution, and that gives you the e to the I ADS2, and then the one loop determinant means just integrating out matter fields around the background. But now what we're going to do is we're going to say we're going to use this. So that was using the exact ADS2 description. That's what Sen did, right? So now we're going to say, okay, actually, if we turn on a small finite temperature and go away from the ADS2 region, there are actually contributions to this one loop determinant that depend on the temperature, right? So what we're going to do is essentially, in principle, we could do the full calculation in higher D and expand everything out at low temperatures and integrate all the zero modes. And you can do that in the Sen style, just from the purely higher dimensional point of view. And you never need to talk about JT gravity. So for people who do not like JT gravity, and I know there's probably more than one, understandably so, because it's just a 2D model. But the point is that you will get exactly the same answers, at least in the simple examples where it's easy to do these one loop determinants manually in 4D at low temperatures, you'll get the same results. So JT gravity is just sort of the IR EFT that captures the temperature dependence of these one loop determinants at low enough temperatures. Okay. You have to take my word for it that you get the same answer, but for now we'll just do by experiment, show that JT gets answers that are reasonable. So I think I already essentially alluded to this, but the idea is that you take the far away region to be classical, and you compute some parameters from the black hole far away, and you fix some boundary conditions. You then have to flow those boundary conditions into the throat region, and those supplies particular boundary conditions on the ADS2, right? So there's a 4D boundary and there's a 2D boundary. And so the ADS2 theory that you get here depends on the choices that you made far away where it was classical. So the idea is that there's some EFT that's labeled by some field theory parameters, and those field theory parameters you have to compute doing some simple UV calculation. So the hard calculation is in the throat region, and the simple calculation supplies the EFT parameters, the coupling constants. So there's sort of an RG flow to 2D argument going on. So if you do that and you compute, let's say the JT gravity answer, if you have an extremal black hole that has extremal entropy S naught, so this correction, this is the linear in T correction. So for instance, if you just did Hawking and expanded out the entropy of the black hole at low temperatures, you would get this result, which is linear in T. And then JT gravity, or just doing a higher dimensional calculation, will tell you that the one loop determinant is beta to the 3/2. And roughly speaking, it's a 3/2 because there are the Schwarzian derivative has 3 zero mode generators, and each one is bosonic, so you get a square root of beta for each of those. So roughly speaking, this comes from regulating the one loop determinant. There's some constants here that I dropped. So now if you use this corrected result where you just use these additional one loop determinants, what happens is at high energies, or far away from the extremal bound, you reproduce the Hawking answer. And this beta to the -3/2 starts kicking in once you get below this gap scale. And what this function actually tells you, this partition function, gives you a density of states that actually goes to 0 at 0 energy, which badly deviates from the expected Hawking result. But again, the Hawking result was just a classical calculation or semi-classical calculation. This is a minimal modification that just adds the temperature dependence to the one loop determinants, and you see that the behavior already gets very different. This turns out also to resolve that thermodynamic fluctuation problem because it changes the size of the fluctuations and closer to extremality and fixes that issue with the Hawking quanta below M gap, which is not really a gap scale here. M gap is just an energy scale where something has to be corrected in Hawking's formula. And one proposal is that the temperature-dependent one-loop determinants fix the problem from 1991.
Matt, can you
Yes.
say a few words about how the one-loop determinant is calculated and how it is regularized and renormalized?
Okay, so you have to spend, unfortunately, to explain that, I would have to tell you all about how to solve this Schwarzian theory, which would take a long time. So what you would do is, first of all, so I've given you the classical action of the Schwarzian theory, right? So I would integrate this thing from 0 to beta, and there could be a number here. This number, a coupling constant of this theory is exactly M gap. You would get that by doing the higher D calculation. This phi b will end up being M gap, right? So I gave you the classical action. Now, what I didn't write was the path integral measure. So you have to show that the natural measure for this JT gravity theory, or in higher D, the natural measure over the space of these modes that are non-normalizable when you set the temperature to 0, you have to show that that natural measure is essentially diff. So this f of t, you could think of it as a diffeomorphism of the circle. So I will integrate over all f of t's, which are diff S1. So the integration space is diff S1, but I have to manually remove the 3 SL2R0 modes that the action annihilates. So when I write down the correct measure, I either derive it from higher D, or I show that there's a natural measure from this T. Oh, sorry, where's the TQ of T? Yeah, so this TQ of T also naturally comes with a symplectic measure from the gauge theory point of view. So the idea is that I have to integrate over all these modes mod SL2R. I then mode expand f of t in Fourier modes, manually remove the 3 SL2R generators, and then I have to do one more thing, and that last thing is that the appropriate measure for this Schwarzian theory, it's actually a symplectic measure. And so Stanford and Witten show that the essentially this path integral for the thermal partition function of the Schwarzian theory satisfies the axioms of the Doistemont-Heckman theorem, and it can be computed by fermionic localization. There's no supersymmetry here, but there's a hidden supersymmetry because the integration space is a symplectic manifold. So this is probably a lot of stuff to just be saying, but the key point is that the Schwarzian theory, I can compute the path integral exactly by plugging in the saddle point value of f of t, which is just the constant round f of t, and then I can expand this derivative. I can expand the Schwarzian derivative with the small fluctuations around that saddle point, and then do the integrals, which are now Gaussian. So I'm utilizing the fact that this Schwarzian theory is somehow solvable. This path integral is a very special integration space. Yeah, it looks like it should be impossible to solve as a Q of t. But the power of this Stanford-Witten paper, which I haven't cited here, but will cite later, is that this is an exact calculation in 2D. It's not an exact calculation in 4D, but it's an exact calculation in 2D. And you can derive that measure, that integration measure, directly from the 4D calculation as well. That was done in later papers. Okay, I hope that was satisfying. That was a lot to take in, but that would have itself been a whole secondary talk. So thank you for the question if people were confused. Yeah. So it just turns out that when you integrate over all those Fourier modes, you get a divergent answer, and thus you subtract out the beta 3/2. And so basically up to a diverging renormalized factor, you just have a beta to the 3/2. And there's some constants. So that comes from regulating the one loop determinants. Okay, let's go to the supergravity case, because that's what I know that's what the people really want to hear. So I've already used up half of my time, so I should probably really race through supergravity to get to the new step. So Strominger and Vafa said that you could count open string bound states given macroscopic charge. If we count let's say, bound states that satisfy this BPS bound, which is also for the extremal black holes, they're able to, by some, let's say, 2D CFT calculation, extract S Bekenstein-Hawking. So this is a extremely famous result in the subject. But the problem is, of course, these extremal black holes were exactly the case where Hawking's formula did not work, right? And you see that this non-supersymmetric answer predicts that you don't get e to the s naught microstates when m equals q, but you actually get very close to 0, essentially. So why did Strominger-Vafa get exactly Hawking's result? SBH is S naught in the previous slide. Why did they get exactly Hawking's result when Hawking's result was not even supposed to be valid? So that's what we explained in 2020. So we essentially considered 4D n equals 2 supergravity, and we take exactly the Einstein-Hilbert, Einstein-Maxwell theory before, and we add the gravitinos, right? So this theory is if the gravitinos are set to 0, it has the same black hole solutions, but now the ADS2 black hole will have additional killing spinners. So there are some preserved supersymmetries, and you can compute the killing spinners, and there's some functions. And so the relevant group, in some sense, so before I emphasize that there's this SL2R, and I had to divide out the SL2R zero modes because there was an SL2R group of symmetries that acted on the ADS2 solution. Like in the ADS2 limit, there was an SL2R. And now what I'm saying is that in supergravity, the ADS2 limit has a PSU 112 algebra. So it's SL2R extended with SU2 rotations of the horizon, extended with supersymmetry generators, which is known as the small n equals 4 superconformal algebra. So this is also the same supergroup preserved by the BTZ black hole in the ADS3 cross S3 cross T4 case. So everything that I'm about to say about the black holes with PSU 112 symmetry, it will be an identical conclusion for the D1, D5. I chose 4D because it was conceptually simpler to compare, but you can do the BZ to Z, and that will come in the second half of the talk. So the idea is that if you want to try to derive some JT gravity, again, you can do the calculation in 4D without ever talking about 2D. The 2D is just gives an intuitive picture of what's going on. The idea is that you could do some Kaluza-Klein reduction where you introduce some field chi and you introduce some gauge fields of this general form. So this is sort of a 4D metric that we've written in terms of some unknown 2D metric. And this HMN is the round metric on the sphere. And the idea is that this additional scalar field that we had, it should be the case that it reproduces the extremal answer to leading order, but then there'll be a small fluctuation away from extremality. So we're sort of writing down a family of metrics, which is almost the extremal metric, but fluctuates away just a little bit by a scalar field. So, okay, this is like a little bit ad hoc, but this is sort of dimensional reduction from ADS2 cross S2 down to some ADS2 theory, but we can allow small fluctuations from ADS2. That's what this is doing. So if you just plug this in and turn the crank, you will literally find from the 4D Einstein-Maxwell action, you do all of the super Einstein-Maxwell action, you will get the JT term as before, but with an additional BF term. So the gauge fields that we introduced in the Kaluza-Klein ansatz will add some extra TQFT that looks like a BF theory. And then there'll also be corrections that are suppressed as the area of the black hole becomes large. Now, there are also fermions that I didn't write here, so I said the full supergravity, so you also have to dimensionally reduce the gravitinas, and that's a big pain. And then the final action that you get is a complicated interacting Lagrangian between 2D gravitinos and these gauge fields and the curvatures. So I didn't write the fermions, but trust me when I say that you can take the spin in the first order formulation, you can take the spin connection and the field binds and the new gauge fields that we introduced and the gravitinos, and you can combine them into a PSU 112 BF theory. Just like before, JT gravity could be written as an SL2R BF theory. This one has a PSU 112 BF theory. So we repeat the same thing with supergravity, and we allow gravitinos to fluctuate. So now, what I told you before is that the path integral could be computed by localization. So just in the interest of time, I won't go through all of the details again. But the idea is that we integrate over some bosonic fields and some fermions, and we divide by the SL2R, the PSU 112 isometries. And you can show that this thing, using the Stanford-Witten paper, reduces by this Dusamont-Heckman theorem to a product of the one-loop determinants for the various fields with a sum over fixed points. Now, unlike in the simpler case before that was just SL2R, now there are actually families of solutions that are included, families of saddles, because the gauge field can wind around. As you go around the disk, the gauge field can wind. And so we have to sum over those different windings. That just follows from the exact path integral calculation. So if we use the 4 supercharged Schwarzian theory and work this out in detail, we get something that is qualitatively similar to the simpler case where we had e to the s naught plus some linear in t correction, but now there's an additional gauge field, and so we have an additional holonomy. This is really the angular velocity in 4D. So we compute these one loop determinants with this additional holonomy, and so we find that SL2R has bosonic and fermionic determinants, and to regulate them, that ends up giving a linear power of beta. And then there's a dependence on the chemical potential, which comes from the SU2 gauge field path integral, as well as the fermion path integral. And this exponential is the same classical action as before. Okay, so if you do the calculation, so before, this is the answer I gave you. If you just throw the fermions out by hand, and just do Einstein gravity and look at a sector of fixed spin j equals 0, you'll get the same kind of answer that we got before, and which fixes that thermodynamic problem, but gets the Hawking entropy wrong, or gets the black hole microstates wrong. If you use the supergravity answer, you find that there actually is a gap scale, and that gap scale, well, okay, so first of all, sorry, let me follow my slide. So there are non-perturbative effects that probably resolve this edge here. And so this calculation is not a full quantum gravity calculation. It's just including the one loop effects. And if we had a full quantum gravity calculation, we might be able to say something about what happens really close to the edge. But essentially, there are no non-supersymmetric extremal black holes, according to in this approximation. In the supergravity case, there is, because of some miraculous properties of the fermion one loop determinants, you will find actually that there exists an extremal delta function of states whose height is exactly e to the s naught. That follows from the Laplace transform of this function. And it's very surprising that there's sort of an extra pole in the Laplace transform that we can interpret as the supersymmetric black hole microstates. And then between the extremal delta function and the non-extremal black holes, there is a gap. And this gap scale was exactly the one argued for in Maldacena-Strominger and Maldacena-Susskind. And they were in the context of D1, D5. But as I said, even though I set this up as a 4D calculation, the same plot, you would get exactly the same plot for D1, D5. And you would relate this phi r to the heat capacity of the BTZ black hole, which is what Maldacena and Strominger got using the affine PSU 112 symmetry. So that's very impressive that a gravity calculation reproduced. So Maldacena-Susskind says that this reproduces the mass of the first non-PPS string, and Maldacena-Strominger says that this reproduces some result that uses the affine SU2 symmetry of D1, D5. So that's very impressive that you got the same number and we got the same extremal entropy. In my mind, this validates a little bit using all of these EFT arguments, using this two-dimensional gravity theory that's very popular but didn't have any obvious connection to higher dimensional black holes. I feel that this result somewhat vindicates the approach because it reproduces things that we knew from string theory before. And it gives like a gravity explanation for why you would get those effects, whereas Hawking's calculation couldn't explain any of this stuff, which had been argued in string theory. So in a sense, in my mind, this vindicates the Strominger-Vafa calculation because it actually gives a derivation of the degeneracies. And it also explains why these degeneracies are not inconsistent with other arguments coming from Hawking and Preskel and others.
Matt?
I should pause here because I need to now race through the whole rest of the talk. So this is a super important slide. I'm now going to be doing this in a much more complicated example that gives a much crazier looking spectrum that it would be nice to derive microscopically. So are there questions on that?
Yeah, I have a question about the gap scale.
Yes.
So you say polynomial in S. So I want to ask a question about BTZ. Okay.
Yeah.
So for
this
the
is
BTZ,
1 over central charge.
Okay, but that's not S naught, right? Because S naught is the central charge times the L naught of the left movers in BTZ. So do you mean S naught or do you mean N1,
Oh, sorry.
N5?
I was using my mouse to motion. The gap scale is 1 over C, which is what you would get from this, large, which was what you get from this Virasoro type argument, super Virasoro argument. And e to the S naught is the usual formula for BTZ. Yeah. You get exactly the BTZ S naught, and then you get exactly the gap scale, which has this, characteristic 1 over C in it.
1 over C, but 1 over C and 1 over S naught are not the same thing.
Exactly. And this phi r and S naught are not the same. The S naught is sort of a parameter of JT gravity that you compute from the UV theory, and the phi r is a different parameter. So this is the coupling constant of the theory. The coupling constant of the Schwarzian is phi r, and the coupling constant of, quote, quantum gravity is S naught. So this isn't including wormholes or anything like that. Wormholes are counted by this S
I'm
naught
not asking
parameter.
about wormholes.
I didn't think you were, but
I was just asking
yeah.
about the distinction between S naught and phi r. Okay.
Yeah. I mean, this is the entropy and this is the heat capacity.
Do you get the factor of 2 correctly? So, for example, when I computed the waves above superstrata, I got a 2 over N1 and 5, which is exactly the factor of 2. Do you get the factor of 2 as well, or you just get a 1 over N1 and 5 with
we get exactly the Maldacena-Strominger result. That's determined by Virasoro symmetry. Super zero Snorr
Does it
symmetry.
have the factor of 2 or not?
There's a factor of 8. The 8 was important. If you know the 8, then that's the same 8.
Okay.
I'm not sure about the factor of 2. I'm sorry.
No, it's 2 and 5. So when you write it in N1 and 5 numbers, it's 2 and 1 and 5 times 1 over Ry, but
Yeah.
it's an Ry. I mean, E gap depends on Ry. You have to put the radius 3 in a box. It's not.
Okay.
Yeah. Anyway.
Let's discuss afterwards. I mean, it reproduces a paper from like 1996. Like the numerical value is the same. So that's why I believe it is the same. But I'm not sure about the factor 2 because I don't remember the formula for this. That's my mistake. I should have written down the number here so we could discuss it. Okay.
Is there a proof? Is there a proof that supersymmetry always results in the right figure and the lack of supersymmetry results in the left figure?
So what do you mean by like a proof? Because in my mind, both of these curves come from doing a 2D exact calculation of a 2D model and then arguing that the parameters of that 2D model are coming from some RG flow of a UV theory, right? So this one is just if you include the fermion one-loop determinants, it modifies the answer. The right curve is just a much more complicated modification of the left curve. I can show by means of example that if you try other different kinds of black holes, you will get different kinds of curves like this that reproduce the exact microscopic answers. I have not yet found a case, and I've written maybe 5 or 6 papers just doing these kinds of calculations for lots of different examples. I have not yet found a case where the e to the s naught disagrees with the microscopic calculation as long as supersymmetric boundary conditions are preserved. Yeah, so the indices match.
In string theory, there's like this D2, 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 D6 black hole, which is supersymmetric, which is the same as Strominger of alpha. And then you can break supersymmetry by taking a D2, 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 D6 bar. You see this symmetry broken in flat space, but when you put it inside ADS3, for ADS cross S, for example, you don't see the supersymmetry breaking. So the supersymmetry breaking happens when you glue your ADS to flat space, but you don't see it in ADS. Your calculations are fully in ADS, right? So so from your perspective, the D2, 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 D6 bar black hole would appear to be supersymmetric.
So Joseph, the crucial thing is there a fermion zero mode? If so, if there's a fermion zero mode and Susie is basically if the extremal geometry preserves supersymmetry, then when I divide by G, I'm kind of removing some fermion one loop determinants. If Susie is broken, no matter how small, if there's just not that G to divide by, then I do not get some certain denominator of this formula. So my calculation is done in ADS2, but it relies on whether or not there's some UV Susie is broken or preserved.
Yes, but
in the sense of, when I do the fermion path integral, essentially.
So so for this black hole, if you glue your ADS2 to ADS3, it will be supersymmetric. But if you glue your ADS2 to flat space, it will not be supersymmetric. Do you see a calculation between gluing to ADS2 to ADS3 as opposed to gluing to flat space?
So I mean the flat 4D ADS2 cross S2, that thing has a killing spinner that extends all the way out to infinity, as does the BTZ in ADS3. And all I'm saying is that if I turn on a very small finite temperature, the exact Susie is broken, but the gravitinos still know that there's a supersymmetry of the extremal solution. So in both the ADS2 cross S2 and the ADS3 cross S3 black holes, this right-hand graph is applicable. If there's some other example where Susie is the extremal solution, because remember, all of these things, Susie is broken, right? No, because I've turned on a finite temperature.
We're just talking about the extremal solution. I don't care about the non-extremal ones.
Yeah.
Schema solution is a D2, D2, D6 black hole, which is supersymmetric. That's like that's like the Schrödinger of alpha 1. And then the D6 bar, when you glue them to flat space, so in flat space, in flat asymptotically, again, asymptotically flat, one is supersymmetric, one is not.
Right. Then I would suspect the second one has secretly this left-hand plot. That would be my guess based on what you just told me.
The same black hole, when you glue it to ADS3, it actually is supersymmetric. So
so the way to resolve this is to go back to this. So I didn't write the fermions here, but the idea is that when you dimensionally reduce the fermions, you have to know what the UV killing spinors are. And if there's no UV killing spinor, then it changes the action in 2D when you do the dimensional reduction. That's how you would see this.
But your UV is an ADS3 UV or a flat space UV? Again, it's very important for this particular thing.
No, that's what I'm saying. Like, you know, depending on which theory I started with in the UV theory, when I try to write down this ansatz, the action of the effective 2D theory depends on what killing spinors were preserved in the higher dimensional theory. So that's you choose a different starting point and you'll get a different action when you choose this kind of Kluser-Klein ansatz.
But then I'm confused because on one hand, I can have two calculations. Asymptotically ADS3, this beautiful black hole is basically a nice, beautiful BPS black hole. So you have the graph on the right. Asymptotically flat, you'd have the graph on the left. But it's the same bloody black hole with the same bloody brains. Why do I get one to have an entropy, one not to have an entropy, depending on what's happening 15 kiloparsecs away at infinity? Microscopically, it doesn't make any sense. Microscopically, one of them is a nice, clean, it's the same black hole, it's the same D-brains. D2,
even in this example, this is the same. These two black hole solutions are the exact same classical solution. What matters is when I do the fermion path integral, do the fermion one-loop determinants have a zero mode that changes the answer, basically.
But it depends on what's happening 15 kiloparsecs away. So 15 kiloparsecs away, something may happen, and you're telling me that this black hole has zero entropy or infinite or huge entropy, depending on some periodicity of some fermions 15 kiloparsecs away. Because again, the black hole in the asymptotically ADS3 region is identical, is BPS, but if I extend to asymptotically flat space 15 kiloparsecs away, it's not BPS. So if I put the 15 kiloparsecs away boundary conditions on your black hole, if I change those, you tell me the entropy goes to zero. It's just,
Right. So I can't say that I have done this particular example in detail. I can tell you that the answer depends on whether there are fermion zero modes in the extremal solution. Whether that, there are examples where it looks like you should have fermion zero, like there's some black ring examples where you would get the left-hand side, even though it naively looks supersymmetric. It's like when you actually, we're doing a fermion path integral, right? And so the integration space and what I'm allowed to divide by does depend sensitively on whether supersymmetry is exactly preserved or not in the extremal solution.
And even if it's
this is a Euclidean calculation, right? So
even if it's broken 15 kiloparsecs away, that's the thing which intuitively doesn't make sense. Why would my brains have zero entropy or finite entropy depending on what's happening 50 kiloparsecs away by boundary conditions? That's really
that's a fair question. I can't give you a better answer without thinking about it a little bit more, like trying to analyze where exactly the problem comes from.
Maybe we can move on to the new results.
I literally have a whole second talk to give, which perhaps I'll go a little bit quickly and to the controversial results later. So let me go through this quickly, right? So I basically explained there's an SL2R gauge theory, there's a PSU 112 gauge theory. We can essentially plug in all these different supergroups. So we can try doing this JT gravity type calculation with all these different supergroups and use the Dussevant-Heckman theorem. So for all these cases, using this gauge theory description, we can compute the JT gravity partition function. And in some cases, the theory you get is just not unitary. So what is the setup? So we're going to essentially use this writing JT gravity as a gauge theory. You can expand it out in components. It looks like Schwarzian coupled to particle group manifold coupled to gravitinos. You can do the same calculation I explained before, and you can, for arbitrary supergroup, compute the partition function. So here's the technical result. There's some power beta that depends on the number of bosonic and fermionic generators. This part is this part is the one loop determinants of the gauge fields coming from the internal space. This is the one loop determinant of the gravitinos, and so you have to sum over the weight lattice of in the representation that the gravitinos transform in, and then this classical action is exactly what you would get from the Einstein gravity in the Hawking approach. So you can compute this partition function, which now depends on potentially many chemical potentials, for an arbitrary supergroup. And so this is the most general result you could have for any super JT gravity. So now, when you actually take this answer, Laplace transform it, and ask which theories give you physically sensible results, OSP N2 does not, SU111 N greater than 2 does not, OSP 4 star 2N does not. All of these are either non-unitary or they have a nonlinear algebra of charges. PSU112 is okay. That's the example I explained. D21 alpha is okay. That's an example that will be realized by the ADS3 cross S3 cross S3, and then G3 and F4. So technically, the first and final two, you could allow them ADS3 if you allow nonlinear superconformal symmetry, but I don't know how to realize them in higher dimensions, so I'll ignore them. So the idea is that just from plugging in different supergroups, we can find that there's actually a restriction on the number of supercharges you can maintain, which is 4. And above 4 supercharges, you start to run into problems. So D21 alpha is the example that we're going to study. So, okay, so now on to the main part of the talk with only 7 minutes left.
No, this is a circular talk, so we actually took, I mean, we allocated you 1 hour and 20 minutes at least, so, you don't have 7 minutes.
Oh, okay. Well, this might be even a little bit longer than that, so we'll see. It depends on how many questions you ask here.
Keep asking questions. If it's interesting, we'll ask questions. All
right.
Don't worry.
Okay, then prepare to ask questions. Okay. So I gave this example of the ADS3 cross S3. I explained that it reproduced some known lore about the theory, including something that is not strictly speaking protected, which is this gap scale. So that was supposed to be a success story in which we say that using this 2D gravity, which again, the 2D picture is not really essential. You can do the calculation in higher D. It's just the 2D kind of makes the calculation easier to organize and allowed us to sort of classify different possible results in a very efficient manner, right? So if we take this D21 alpha example, that is a very interesting spectrum. And D21 alpha is a symmetry of this ADS3 cross S3 cross S3 cross S1 solution. So I need to review a little bit about this solution, the brane constructions, and then I can apply the D21 alpha result to make some predictions for this theory. Okay. So there's a remarkable background of type 2b, and it realizes the so-called large n equals 4 superconformal symmetry. So before there was the small n equals 4, and I emphasized that there was a single SU2 gauge field. But with large n equals 4 supersymmetry, there's roughly speaking an SO4 R symmetry, and SO4 is the same as SU2 cross SU2. And in the case that I did before, one of the SU2s was essentially inert. It was an outer automorphism. In large n equals 4 symmetry, both SU2s play a role. And you can see that, of course, it's already hidden here. The fact that I have an S3 cross S3, really there's a bunch of SU2s. And if I take only the left-moving guys, for instance, then there'll be sort of 2 SU2 R symmetries, or 4, depending on exactly how you're doing the counting. But there are 2 non-trivial SU2s in this theory. And it was first discovered actually quite a while ago. Maybe not discovered, but the most useful references that I studied were these Boonstra, Peters, Skenderis, Gauntlet, Myers, Townsend, and De Boer and Skenderis. And then for discussions of the dual CFT, there was this very important in reference, Gukov, Martinick, Moore, and Strominger. And they were essentially in their paper they discussed the ADS3 vacuum, explained the large n equals 4 supersymmetry, and they were trying to derive a dual CFT or find, the quest for the dual CFT. So one reason why this background is interesting is because the large n equals 4 SUSY seems to be the most that you could have a black hole preserve based on this, JT gravity type calculation, but it's nevertheless true that large n equals 4 is essentially the biggest superconformal algebra that isn't nonlinear. And there's a supergravity solution that has the large n equals 4, this D21 alpha as an isometry, but we don't exactly know the dual CFT. So the cartoon is that as the D1, D5, D5 prime, but there's a big asterisk here. So for instance, Tong tried to derive the CFT from the intersecting branes, and he got an answer that is not quite correct. I mean, it relies on some argument that is not totally clear. Yes.
D1, D5, D5, D1, sorry, D5, D5 prime D1 or D5, D5 prime F1? Because
we could do S dualities on this. I'm choosing the D branes right now because I will ultimately do Ramon fluxes, but there's an NS sector version, right? So just for now, we could think of this as the D1, D5, D5 prime, but if you literally choose these to all be D branes that intersect orthogonally, then the final factor is R and not S1. So to get an S1, you sort of have to sort of dissolve one set of D5s. So really you should think of it as a D1, D5 system in the background of D5 prime flux. That's the most precise version that will give us the S1 for sure. And it's also the one that was important for Edward's recent paper where he tries to construct the CFT in 2024. So for us, there's an S1 and one of the D5s is actually D5 flux. The story with this 2004 paper is that it was a heroic attempt to figure out what the dual CFT is, but there's a lot of weird properties of the supergravity solution that are hard to explain with, for instance, a symmetric product orbifold, right? So in the usual D1, D5, there are good arguments that the theory, there's a point in the moduli space where it looks like a free symmetric product. That's not so for this ADS3 cross S3 cross S3 cross S1 background. Only if I choose some fluxes to be very special could it be a symmetric product. That was one of the conclusions of this 2004 paper. Okay, so this is a problem where the supergravity background has been known for like 30 years or something, but the dual CFT sort of remains unknown. Maybe Edward has nailed it with his recent paper, but this is sort of an open question if his CFT is the correct one. So there's a sort of reason why this is a confusing theory, right? So the first is that if we just look at the ADS3 cross S3 cross S3 cross S1 and compute the analog of the global algebra, right? The global isometries of this solution. So that has a D21 cross D21 alpha symmetry where this D21 alpha appears in the classification of superconformal algebras, and there was the one that appeared on our paper, and it sort of has its SL2R with two SU2s. And this alpha is sort of a continuous parameter that controls the weight of each SU2. I'll write down the algebra in a second so you can see where alpha appears. But the point is that this algebra has the standard set of commutation relations, and it has a standard BPS bound that you can extract from the algebra. Now, if we embed this in, if we look at the affine or the local conformal symmetry, the super Virasoro, then we have the, sorry, I need to hide floating media controls. Yeah. Okay. So then we have this thing called A gamma. And unfortunately, there's some notational confusion, but gamma and alpha are related to each other by like gamma equals 1 over 1 minus alpha, something like that, right? And so this A gamma denotes the Virasoro extension of D21 alpha. And this is, again, it has standard linear algebra and standard commutators, but it has a nonlinear BPS bound in the sense that E goes like J squared, something like that. So this nonlinear BPS bound is just a funny property of the large n equals 4 algebra. It did not show up with any less supersymmetry. So you can see that the BPS bound, because this one is linear and this one is nonlinear, it means that in general, the BPS bound for D21 alpha does not agree with the BPS bound for A gamma. And, oops. And just as a side comment, if we had more than 4 supercharges, then the algebra is nonlinear and the BPS bound is nonlinear. That's why we excluded them from the table before. But this large n equals 4 is an example where, in principle, the symmetry algebra is an ordinary linear algebra rather than one of these nonlinear W algebras, but the BPS bounds between the global and local don't agree. This was a big puzzle for de Boer back in 1998 and in a subsequent paper. So the fact is that the BPS bounds mismatch due to this nonlinearity. And so when de Boer and co did the NS sector supergravity computation, so just do the Kaluza-Klein mode expansion on S1 cross S3 cross S3 cross S3 cross S1. If you just collect the Kaluza-Klein modes, you could choose to try to organize them in terms of the D21 alpha primaries, or the affine n equals 4 superconformal primaries, and you seem to get different answers. So they were kind of confused by this. This was similar to a talk we had yesterday, in which sort of the counting of the global primaries versus the local primaries could in general be a little bit different. So this is just from the supergravity point of view. There was already a confusion with this. And so this problem was hanging around for a long time and was resolved in 2017, essentially from two different approaches by Eberhard and collaborators, and then also by this group. And so what they were able to show is that these two BPS bounds between the global and local algebras, they agree when J plus is equal to J minus. So the J's are the two spins on the S3s for BPS states. And so it was argued doing the supergravity carefully from the world sheet point of view and using integrability that at least in the NS sector, if we just look at fluctuations around the ADS vacuum, J plus has to be equal to J minus, results in the BPS bounds agreeing. And they found that all NS sector BPS states have this property. So the confusion was resolved by forcing this restriction on the NS sector. Now, the Ramon sector was not discussed, and I think it was believed that you could just spectral flow, but there's no dual CFT, so we don't really know the Hilbert space of this theory. We know some constraints on the charge spectra of BPS states, but we don't really know the full Hilbert space of this theory. And so no one understood the Ramon sector. The Ramon sector, of course, it can contain large supersymmetric black holes. And it was never completely understood, even though in principle spectral flow should relate them to the NS sector. So the idea is that, JT gravity naturally gives you a prediction for the Ramon sector. So we'll use our JT gravity results that I motivated in the first half of the talk to make a prediction for this theory that has this D21 alpha symmetry. So that's the story. There was confusion already for 20 years in the NS sector. It was resolved by putting a restraint on the charges. We'll now see the R sector obeys a different constraint, which naturally comes from looking at the black holes.
Two stupid questions. First of all, you have two S3s. I have an SU2 right and SU2 left on each. These J plus and J minus are in the, so you have two SU2s on each. So those are SU2Js or they're normal?
Yeah, sorry, these are SU2Js. Yeah, so these BPS states, they have M equals J, and then they also have only their left-moving SU2s turned on. So these are like left-moving BPS states, M equals J, and this J plus is the carton of SU2 left, and this is the carton of SU2 right. So this will be more clear when I write the metric. There are indeed a bunch of SU2s. And this is some particular carton where I've turned on the spin on S3 and a spin on S3, both left movers.
And spectral flow normally involves a mixture of the time with one of the angles of S3 when you have ADS3 times S3. Here we have some more fancy spectral flow which involves both, or which one?
Yeah, there is a more fancy spectral flow, and I actually don't understand it very well. The best case is to try to look at Emil's paper from 20 years ago. But we don't have a microscopic CFT, so that there exists some spectral flow just because this large n equals 4 algebra has a bunch of SU2s, but that won't play a role here. We're just going to do the Ramon sector calculation by assuming the black hole provides the dominant saddle point contribution, and we'll find a different answer from this one. Okay. So if I had a CFT, like a free CFT, or I had some description of the Hilbert space, then we could check how spectral flow works or how this fancier version works, but we don't really have the microscopic theory. This is a case where we only have the gravity solution, essentially. And an argument that the gravity solution comes from the decoupling limit of these D branes, but there's no formula on the brane world volume theory. The best case scenario is to use Edwards' proposal, which was from a year ago, but it's rather complicated. So I don't know how the fancy spectral flow acts. We're just going to do the Ramon sector in vitro, and we'll get different answers that maybe will surprise you.
Yeah. So in n equals 4 Yang mills, for 1/16 BPS states where there are black holes, there are similar sorts of constraints on
bingo. Thank you.
Charges. So
yes, that's coming just a second. Yes, okay. Perfect. Exactly. So this constraint on the charges came from doing the Kaluza-Klein expansion very carefully. And that was done by Lorentz, essentially, doing this KK expansion very carefully and showing that the earlier result by de Boer doing the KK expansion and organizing things into D21 alpha multiplets was incorrect. And so the careful supergravity calculation just in the vacuum gives you this kind of charge constraint. But the black holes, as you know, in order for the black hole to be both supersymmetric and extremal, there's a similar constraint, which could be a nonlinear constraint. So in the case of ADS5 black holes, there's a nonlinear charge constraint that determines the BPS ones. We'll get to the analog of that in just a second. Yes.
Okay, thanks.
Great question. It's coming. Yeah. And, oh, sorry. So if you want to do things with the pure NS fluxes, so we coordinated, so our paper appeared on the same day with Samir and Mukun's paper. So they consider this ADS3 cross S3 cross S3 cross S1 in the, with pure NS fluxes. They study the world sheet theory, and they do a very different world sheet calculation, and they're able to get the same BPS spectrum as us at the end of the day. So these results, you can derive them, the results that are coming, you can derive them from the black hole point of view and this JT gravity with computing the one loop corrections around the black hole, or you can derive them from string theory using the world sheet theory. But of course, one works for NS and one works for R. They're complementary pictures. So now I'm covered because now I tell you that everything was derived from string theory, so you have to believe me from now on, right? All right, but let's see. It's a surprising result. Okay, so now I need to say a little bit about the theory. So we're going to only use Ramon fluxes, and we'll use D5 and D5 prime. So we'll write down the type 2B action. There should be a 10 here, and the dilaton will normalize it to give us some constant, and then the vacuum solution will look like this. So we have a unit ADS3 with length L, and we have an S3 with R plus radius, and an S3 with R minus radius, and then we have an S1 with a length L. And I'll write down the relation between all these parameters, and then there's also flux. So there's Q1, Q5, Q5 prime, where these epsilons are volume forms on the S3s and the ADS3s, respectively. So I guess this is probably familiar. Now, in order to solve Einstein equations, it looks like there are more parameters in this metric than should be determined. But the point is that if you take this ansatz and try to solve Einstein equation, there's a sort of nonlinear relation between the ADS radius and the two S3 radii. The S3 radii are determined by the fluxes that I started with. So this is all fairly familiar so far. We just have an extra S3, basically, right? So which leads to a slight complication in the ADS radii. But this kind of formula is part of the reason why this theory ends up being very complicated, because there are two spheres. You can kind of do things asymmetrically on each sphere. So in terms of this D21 alpha, or this large n equals 4 superconformal algebra, I told you that there's two SU2s. So there's two affine SU2 symmetries, and their levels are determined by these combinations of fluxes. Now you can determine by the Brown-Hanot central charge. So again, this is in supergravity. So the Brown-Hanot central charge is related to the levels. And you can see that in general, this central charge will be some rational number, right? And so it's hard to reproduce this sort of very general rational number from a symmetric product orbifold description, right? I mean, this is just going to be hard. You know, if you had free bosons and free fermions, you might get integer or half integer central charge times 6. But this thing, you could get wildly, very weird irrational numbers, very weird rational numbers for the central charge, which seem like it's hard to do this with free bosons and free fermions. And then this alpha parameter of D21 alpha is just the relative radii of the ratio of the radii of the spheres. So this is a funny example in which the symmetry that the solution preserves, the symmetry algebra is a one-parameter algebra, and some classical looking information like the size of the S3s actually determines the symmetry algebra. The algebra depends on R's, essentially. So that's very crucial, because in string theory, this is the funny thing, right? In string theory, Q5 plus and minus are quantized. So alpha has to be a rational number. But in supergravity, when these are both large, alpha is a continuous parameter. So we'll see other cases where there's some conflict between sort of a parameter that secretly is discrete and a parameter that looks continuous in supergravity. And we can see that the supergravity calculation is sensitive to alpha being rational, even though it sort of has no mind to it, essentially.
Matt, can you say what the dilaton is?
Yes.
Can you say what the dilaton is?
Yeah, I think we normalized it. I mean, I didn't write G string here, but I could have put G string squared here. I called it just G string. We could normalize it to 0 here. This is Ramon fluxes. So the dilaton has been set to constant, and e to the dilaton is 0. Yeah. It doesn't play a role for these fluxes. Yeah. Okay. So let's review this large n equals 4 superconformal algebra. I already talked for 10 minutes about the large n equals 4 superconformal algebra. It's time to finally present it. So this A gamma, it has the usual. So there's a left and right moving copy of this. So let's just look at the left movers, for instance, right? So the A gamma consists of the usual Virasoro generators. And then there's supercurrents that transform these capital A indices, they're SU2 indices. So the supercurrents transform in bifundamentals of the SU2 cross SU2 left moving symmetry. And then there's gauge fields that are in the adjoint of SU2, and then a gauge field's in the adjoint of the other SU2. So this is all the stuff that you would kind of expect just from writing down the ADS3 cross S3 cross S3 solution, right? I have some fermions that transform as bispinors. I have some Virasoro, that's our for the usual Virasoro, and I have two SU2s, so I should have two kind of sets of currents like this, right? The surprise is that this algebra on its own, I could write down commutation relations for algebra, a local algebra, just with these generators. The global part of this gives me D21 alpha, but the local part actually has nonlinear. When you take OPEs of these currents, there's going to be nonlinear terms in the OPE. And this was discovered by Knisnik, I don't know, in the 80s or something like that. So if you want an algebra, a current algebra, if you want a super Virasoro algebra that actually has only linear terms in the generators, then we need to add extra matter to this algebra. So this large n equals 4 superconformal algebra actually should be called the extra large n equals 4 superconformal algebra, because I have to add an extra set of spinor currents that are bispinors, which I call Q. And I also have to add an extra U1 symmetry, which is related to the sort of U1 translations of this circle, and also U1 symmetry transformations of F3 shifting this by a flat connection. So that's where these two U1s come from, right? So you might have thought, where was this extra U1 symmetry? From this S1 has a U1 symmetry. Well, it shows up in the algebra as well. And it's actually necessary for there to be a local ordinary superconformal algebra with no nonlinear terms.
But
yes.
I thought the D21 alpha supergroup could have alpha negative. While in all what you do, it seems it has to be positive, right?
I chose it to be positive. This is the convention. It's positive here. If there's some other paper that has alpha by convention be negative, that's fine. I didn't show you the commutators yet, so you can see where alpha enters. When I click this next button, you're going to have all the commutators dropped on you, and then we can see where alpha has to be, whether it has to be positive or negative. And in my conventions, it's positive. Yeah. So anyway, so the circle with the U1 symmetry was essential for the large or extra large n equals 4 superconformal algebra to be a local non-W, non-linear algebra. So this extra matter content is crucial. So the S1 was crucial for us. Okay, so here's the commutators. Okay. So the two supercurrents, this here can be related to alpha and 1 minus alpha, and this can be related to alpha and 1 minus alpha. I guess, unfortunately, I wrote it in terms of Ks, but you can see that the Ks are K minus over K plus. So this is related to alpha and 1 minus alpha, and this is related to alpha and 1 minus alpha. So the supercurrents have alpha built into their commutator. But now these extra supercurrents, these extra Qs, these extended Qs, they also, their commutator is a pure central term that depends on the level. And then there are also non-trivial commutators between different types of fermionic currents that generate SU2 rotations and U1 rotations. And similarly, the level enters when we consider the action of the SU2 on a supercurrent. So this is called the extra large n equals 4 superconformal algebra. Although no one will call it extra large, this is the linearized n equals 4, large n equals 4 superconformal algebra. Any questions on the commutator dump? I know it's a lot. I know it's a little bit weird that we have these extra currents beyond what you might have normally guessed. But this is sort of, as a math statement, this is the correct algebra that describes the S1 version of the theory.
Just want to follow up on Raphael's question.
Yes.
There are papers by Bacchus and Doka and so on, and then the parameter in the D21 alpha thing is allowed to be negative, and it is a distinct superalgebra.
Okay. Oh, so okay. This I didn't understand it then when he asked before. That's my That's my mistake. I mean, in my conventions, alpha necessarily has to be positive because I took it to be the ratio of two charges of BPS branes that were positive, or it's the ratio of two radii, so it's definitely manifestly positive in my conventions. Whether this has meaning for negative alpha, I'm actually not sure.
Do you have like a choice of orientations of some of the D5?
Yeah, I mean it's almost certainly that, but remember for me it's really one set of ordinary D5s in the background of D5 flux. So the D5s are not treated completely symmetrically. It only looks symmetric when you take the back reacted limit. Yeah, that was one of the big puzzles of this background as well. And I guess you guys are working on this from the M theory point of view. So okay. Because I'm now already over time, perhaps we can discuss this issue at the end of the talk, just so I can get through my main conclusion, because I still have many more slides. So let me move a little bit quicker. Okay, so here's the black hole solution. There are basically 4 Cartan gauge fields. So these are A left, A right, plus and minus. So there's plus, minus, and left, right. So there's 4 Cartan gauge fields. This is the non-extremal solution. So this is the most general solution of Einstein's equations that looks like a BTZ with all the charges turned on. So there's angular momenta, which I call the velocity is r minus over r plus. There's a temperature, which is r plus over this combination. And then there are a bunch of gauge fields. So you can check that this is the exact solution of type 2b supergravity. Sometimes I'll also denote alpha plus minus, and they're going to be rescaled versions of the angular velocity. So whenever you see alpha plus minus, this alpha is not the same as the D21 alpha. These are the angular velocities on the spheres. There's also alpha bar that is the left to right movers. So there was a question earlier about what J's are what. The J's are the charges that are conjugate to these 4 different possible potentials. And for BPS black holes, I will have to turn omega equals 1, and that will kill some of these things. And so the J left and J right and the BPS bound was for the left moving A's only. Okay, so this solves type 2b. You can check it yourself. And so now we get to Emil's question about the nonlinear charge constraint. So using this non-extremal solution, this solution is not BPS and it's not extremal. So let's now check, when is this black hole extremal? So we can write the extremality condition in terms of the conformal dimension, and again, these J's. So this is the extremality condition. The BPS condition, which you can check by, say, when is there a Killing spinner in Lorentzian signature, the smooth Killing spinner solution of this classical solution, the BPS bound is different. So you can see that the extremality condition and the BPS condition are not actually the same condition. This is totally analogous to ADS5 cross S5 black holes, in which the BPS condition is, some linear relation among the charges, and the extremality condition is like some nonlinear relation because you have to send the temperature to 0, right? BPS, the condition is just, M equals Q, roughly speaking. Extremality condition is that T equals 0. So extremality is usually a complicated nonlinear formula. BPS is typically a linear formula. It turns out for the large n equals 4 algebra, even the BPS condition is of this nonlinear form. That's when I mentioned before that there's a nonlinear BPS bound. So the extremality and BPS conditions not agreeing is totally normal and happens for all supersymmetric black holes. If we ask what is the intersection of these two, so a causally well-behaved BPS black hole that's also extremal, the intersection of these conditions is the analog of the nonlinear charge relation. And this relation ends up being linear, but there's a catch because it has alpha in it. So J minus equals alpha J plus. That's the classical or semi-classical charge constraint. Now, if you remember before, if you just looked at empty ADS3 and looked at the Kaluza-Klein expansion, there were different approaches that gave us J minus equals J plus for BPS states. Now what I'm telling you is if you just study the supersymmetric black hole, which solves the type 2b supergravity equations of motion, and for any value of the charges, you can write the solution down. Its extremal and BPS bounds coincide for a different limit of J minus equals J plus. So semi-classically, already the charge relation in what will end up being the Ramon sector is different than the NS sector empty ADS3 result. This charge relation is not protected, by the way. This is not a protected quantity, and in general, there are going to be corrections, as is the case in the ADS5 black hole. And so actually, we will give a proposal for what the exact formula for this is, using, again, this JT gravity stuff. Okay, so let's, well, yeah, okay, so sort of plot this, as we tune the ratio of radii of the spheres, the BPS states their angular momentum is concentrated partly along the J1 direction and partly along the J plus direction and partly along the J minus direction. So sort of a picture is if the two S3s are equal size, then BPS states have equal angular momentum around both S3. But if the S3s are very asymmetrical, then almost all the angular momentum is distributed on the larger S3. So again, this is very different than the NS sector, where the top picture is always the case for BPS states. In the sector that has these large BPS black holes, the angular momentum can be asymmetrically distributed. This is just a graphical rewriting of this formula right here. Okay, so let's find the quantum corrections. All right.
Does that arise from some kind of naive analysis of spectral flow, where spectral flow would naturally come in units of the level of the SU2?
Yes.
And
yeah,
so if I spectral flowed
the
NS formula to Ramon naively, I would develop an asymmetry in the angular momenta simply because of that fact, right?
Yes, yes. But this, I mean, this relation is not even it's not an exact relation. This is not an exact statement about BPS states. This is really a semi-classical formula. So spectral flow is something that is a true isomorphism of Hilbert spaces, but I wouldn't expect to derive this just from the algebra alone. Or equivalently, I had to use Einstein's equation to derive this formula. So you shouldn't expect this to come exactly from some argument involving the spectral flow.
Okay.
Is that correct? I'm honestly not sure. I was hoping maybe after the talk, or maybe after Raphael's talk, I could hear what you had to say about this. Because we were really puzzled by a lot of these large n equals 4 things. I think in the end we are confident that our result is correct and interesting, but there are definitely certain aspects that I can't completely explain. In part because we don't have a free large n equals 4 theory where any of these things can be tested in an explicit way. We have the gravity solution, and we know that a lot of things are not actually protected. Some of them are, and we'll see the protected things are interesting as well. Okay. Yeah. So let's now do the JT gravity calculation. So we already belabored the point. So alpha is related to gamma in this way. So this is the D21 alpha. The idea is that there's sort of a different JT gravity for every value of alpha, and alpha appears explicitly in the coupling constants for this theory. So the bosonic part I wrote, there's a phi r, which we compute in the semi-classical theory. I mean, we just compute this from the classical gravity analysis. This is the heat capacity of the black hole that I showed you before. S naught is the extremal entropy of the black hole that I got before. And then the gamma is related to alpha in this way. And it's sort of the coupling constants of these two SU2 gauge fields. There's also a U1 gauge field, because remember, we're doing the extra large algebra. So there's a U1 here. And I wrote plus fermions. If you add the fermions, the formula wouldn't fit on multiple slides. It's a super messy action. We're going to really use localization to avoid having to write the component action and do calculations with that, because it's way too hard. So the idea is that the path integral will compute this partition function. Okay, so why am I using JT? I already spent 30 minutes telling you that. You have to just trust that it's going to give something interesting, and then we can discuss if it can be reproduced in dual CFT. So I'm just assuming that this calculation will work based on the arguments I gave earlier, right? So the claim would be that this path integral over these different fields, the SU2 gauge fields, the Schwarzian field mode, the U1 field, if we do the path integral over these guys plus fermions, it should be computing a partition function that depends on the inverse temperature, these two chemical potentials, alpha plus and alpha minus. So remember, these are related to the left moving angular velocities on the two S3s. And then U is a chemical potential for the S1 gauge field that we have in principle in S1 symmetry. And it computes in principle this trace over the Hilbert space with J3 plus and J3 minus, and capital U is the U charge. So that's the setup. Of course, JT gravity doesn't have a microscopic interpretation of a trace, but this is morally, it's computing the approximate large N growth of this trace. Okay, so I'm just going to present the result because I'm way over time and I want to, so the idea is that you use the Doistemont-Heckman formula. This classical action, this is actually exactly the classical action of the black hole that I gave you before when you expand it at low temperatures. So you could derive this just from 10-dimensional type 2b, which is what we did. The exponent you derive from 10-dimensional type 2b. The one-loop determinants, we have to use this JT gravity description because we don't have a better way. Oh, okay. We do have another way. You can also get this from the large n equals 4 Virasoro character. So if you do a modular transformation of the vacuum Virasoro character, you can expand at low temperatures. You can also get these one loop determinants. We really actually computed this thing 3 different ways, and they all give the same answer. So the one loop determinants, there's some power of beta, which is determined by regulating 0 modes. Alpha now enters the one loop determinants, this up alpha. This is the D21 alpha alpha. And then there are SU2 gauge field one loop determinants. There are fermionic partners. These were the Qs that appeared in the algebra before. And these are the gravitinos. So just explaining how we got this would be like the whole talk. And of course, it would be very like just complicated explaining the calculation. Just trust that the result we got is reasonable and is an exact formula because of the Duisterman-Heckman theorem. Okay, so as I said, you can compute these one-loop determinants without ever talking about JT gravity. You can do the Maloney-Witten style analysis, and you get exactly the same thing. It's in the appendix of our paper. It's doing a modular transformation and expanding it at low temperatures. And the thing that you modular transform, it's naturally the NS sector partition function with -1 to the F. So this is giving us a prediction for the Ramon sector. From the 2D CFT point of view, this is a prediction for the Ramon sector, following the Maloney-Witten style analysis. And these MNs, these are the sums over spectral flow. So spectral flow is hidden in this formula. I said that we didn't like completely understand it, but you can interpret this sum over integers from the point of view of the Virasoro character as a sum over spectral flows. It's just they're integer spectral flows, not half-integer spectral flows, or not spectral flows that are depending on K. So the spectral flows are in this formula. You can get this from this Iguchi-Taormina n equals 4 supercharacter story. But you can also get the same thing from JT gravity. The two things are really the same theory. Anyway, okay, so now we want to do this Laplace transform and get the density of states and make the plots. We all want to see the plots. Where's the plots? Okay, so what we should do is we should organize the partition function in terms of this inverse Laplace transform of a density of states. So this is crucial. So first of all, the states need to transform in representations of large n equals 4 superconformal symmetry. And so there are 2 types of multiplets with large n equals 4 supersymmetry. There are long multiplets and there are short multiplets. So these things are just SU2 characters, are really they're SU2 cross SU2 cross U1 supercharacters. I won't even write them, but they're just sums of exponentials that take care of the n equals 4 representation theory. So each of these characters just contains a family of states related by supersymmetry. The long multiplets are not BPS. The short multiplets are BPS. Both involve a sum over a charge lattice. So the partition function has a sum over charge lattice weighted by these characters, which contain the fugacities for the angular momenta and the U1 charge. And then the microscopic microcanonical density of states for the continuum is over here. So for the long multiplets, this row will end up being continuous, and it depends on the energy. For the short multiplets, normally this is just a number here, right? The short multiplets have E equals 0, and it's that delta function from the first slide. What happens is that actually we see that there's a BPS energy, and then there's also some degeneracies. N's, these are going to be microscopic degeneracies. So the surprise is the appearance of a BPS energy, and also I should write down what this row is. So this is what rho is. So this is the continuous density of states. Okay, it's a super messy formula, but it's a very hard calculation to get to this result. The inverse Laplace transform, I don't want to say how long it took, but it took a very brave graduate student to find a lot of tricks to evaluate this integral transform. So you'll just have to trust that the result is correct, and we numerically checked it and many things like that. So it's a complicated formula. The non-BPS density of states still grows like S naught, but it's times this factor. So these factors. So first of all, there's a sinh, and these JT gravity partition functions always give you something like a sinh or a cosh, and it's related to random matrix theory. There are also various poles, 1 minus E poles, and these come from the fact that there are the large n equals 4 supersymmetry. Basically, the more SUSY you have, the more poles you have. And this is again related to random matrix theory with a lot of degenerate states. Oops, sorry. Now, these long multiplets, they actually start at a particular gap scale. So you will never actually hit the pole that there should be a Heaviside theta function here that says that the spectrum starts at the first pole and starts at the second pole. So there's a gap scale here, and that gap scale is going to be called E naught. So for each of these values of J, for each of the U1 for each assignment of U1 charges, there is a gap scale, and that gap scale depends on the charges. So different multiplets begin kicking in at different energy scales, where multiplets are labeled by their J's and their U. This is probably a lot to take in. It's probably very hard to interpret this formula without showing it in comparison to the other ones. So trust that these kinds of density of states are very common things to get from JT gravity calculations. And the question is, what does it mean for the higher dimensional black hole? So let's now focus on the BPS spectrum. It has these microscopic degeneracies, and then also this BPS energy, which I have to explain. So I told you that the BPS bound is nonlinear. And it turns out that because the BPS bound is nonlinear, the BPS states are not just concentrated in a single charge sector. So in the first half of the talk, I gave an example in which all the BPS states sat at J equals 0. That was the only place that was a delta function. For any other J, there were no BPS states. The BPS bound in this theory, which is nonlinear, allows for different solutions that have different charge assignments. And rather than all of these BPS states having 0 energy, they actually have a ground state energy that depends on the J's. So this sounds almost heretical. BPS states are supposed to be ground states. That law is violated if the BPS bound is nonlinear. And there are actually an infinite number of superselection sectors which have different BPS ground state energies. And it depends on J1 and J2 in this nonlinear way. It also depends on the heat capacity, which tells you that this is a one-loop effect. This BPS ground state energy, you can never get it in the classical theory. It has Newton's constant in it. This might be shocking to people, but let's say a little bit more, right? If we now look at the degeneracies of the BPS states, so the BPS ground state energy says that there's an infinite number of solutions of the BPS bound, and their ground state energies are different, shifted relative to each other. I can't normalize them so they all have 0 energy. If we look at the actual degeneracies as a function of the J charges, we see that we get a nice formula. It goes like e to the S naught, where S naught is this combination of charges Q1, Q5, Q5 prime over, times J. So S naught, e to the S naught, this is what you would get from classical supergravity. But then this factor here that depends on alpha and J is a one-loop effect. Coming from these computing the one-loop determinants of all these gravitinos, it depends very sensitively on the alpha parameter, and it depends sensitively on J's. And indeed, we find that there are just no BPS states if the J's don't lie in a particular interval. So if the J assignment is such that some alpha-dependent function of J lies between 0 and 1, then you will find a large number of BPS states that's kind of modulated by a sign. And if the J's fall outside this bound, that you get 0 BPS states. So this follows from doing the Laplace transform integral calculation. There's sort of some Heaviside function that appears. So I don't have a great intuition for where this comes from, except it's implied by the complicated structure of the gravitino one-loop determinants. But if you think about it, if I'm telling you now that there's a restriction on J plus and J minus, and if this restriction is satisfied, then I find BPS states. And so indeed, this R BPS range is actually a quantum generalization of the nonlinear relation J minus equals AJ plus. And obviously, if you take all the charges to be really large, this BPS condition reduces to this one. So before I said that this J minus equals alpha J plus, it was a property of the Ramon sector. It's not protected, and there can be loop corrections. This is a proposal for what the loop corrected version of the nonlinear BPS bound is. It depends on alpha. And there can be jumps. If we imagine alpha as a continuous parameter and we start varying alpha, classically, varying alpha just meant that the BPS states will slowly distribute their angular momentum between the two S3s. Quantum mechanically, we see that's actually a discontinuous process because this is a Heaviside function. BPS states will jump. Let's look at the jumps. So this NS sector spectrum, J minus equals J plus, these are all BPS states that satisfy J minus equals J plus. And this is the claim, is that the NS sector partition function has this BPS spectrum. In the R sector, these are the discrete jumps. So I drew different colored curves for different values of alpha, right? So this orange line, this is the symmetric value of alpha where the two spheres have the same radii. And this is where I start making one sphere bigger, and this is where I start making the other sphere bigger. And so as a function of alpha, we see that the J plus, J minus distribution changes. Now the straight lines, those are the J minus equals alpha J plus. These are the semi-classical approximation. Whereas the dots, the discrete points, those are the ones that are the solutions of this RBPS, considering that J plus and J minus are half integral, then the dots are like the discrete solutions of the BPS bound. So you can see that the semi-classical curves interpolate between these discrete points that are the exact quantum answer. That's a very nice check to show that this J minus J plus relation in the semi-classical theory, the exact result agrees with the semi-classical limit if I went to very large charges. These points would become very closely spaced and the lines would go between them. Any questions on this? I think I've been talking for a long time. There's only a couple slides left, but I want to check in if people are following, if this was a little bit too much to take in, because this is a very important conclusion that this semi-classical gravity calculation supplemented with one loop determinants has this really interesting kind of wall crossing phenomena in the BPS spectrum, which I've not seen anything like this in other examples. So if people have questions, please ask. Otherwise, I'll get to the last few conclusions.
Maybe you can get to conclusions because again, we need to get some coffee in the system and we have Raphaël's talk, so it will become.
Yep. Got it. Coffee. I know. All right. Okay. So if we just plot these, I gave you these cinch formula or whatever. If we just plot it as a function of alpha, let's say, when alpha is symmetrical, if I look at some particular charge sector, I have these spikes. These are where BPS states are. And the blue curve is the continuum of long multiplets. And so there's BPS energy. So this is telling you that the BPS states can have different ground state energies. And there's also a gap scale as before. And now let's say that I take the same value of the charges and increase alpha to 4/3. What happens is that one set of BPS states disappears from the spectrum and is kind of, sort of resolved by a little non-BPS spike. And then the gap starts to close and there's some smaller number of BPS states. And I increase alpha further, then they both disappear. So this is sort of showing that as I vary alpha as a rational number, BPS states appear and disappear from the spectrum, and the non-BPS states reorganize to kind of fill in the holes in the spectrum. Okay. Now, so there's a whole thing. We could also compute the elliptic genus from gravity. So it turns out that if you choose the angular velocity to be a particular imaginary angular velocity, so this is similar to ADS5 black holes. If you choose all of the angular velocities in ADS5 or all other examples, if you choose them to satisfy an imaginary constraint, and Euclidean signature, this means that you don't have a real metric anymore, but it still solves the Einstein equation and it implements the -1 to the F boundary condition. So in this case, the imaginary velocity is somewhat weaker. We can do it only using the left moving potentials. And if you plug in this imaginary angular velocity, it's actually the same as in higher D, it's the same as computing the index of JT gravity. So we can write down a 10D solution with an imaginary angular velocity, and we can compare that with the index as computed in JT, and we get the same classical part and the same set of saddles contribute. So if we compute the index in JT gravity, we can see that there's actually temperature dependence in the index. So it still goes like e to the s naught with some alpha dependent factor, but there's actually temperature dependence because there's a sum over super selection sectors. Okay, so once again, this may sound like heresy. A temperature dependent index, it follows naturally from the fact that different BPS sectors have different ground state energies, but essentially the nonlinear BPS bound invalidates the usual lore that the index has to be independent of continuous parameters like the temperature. That's just not true for the large n equals 4 superconformal algebra. So reproducing this temperature-dependent index is one of the microscopic checks, at least at large n, that this is correct. And of course, that hasn't been done because we don't have the dual CFT, but finding a localization calculation that could give you this kind of factor is very difficult. But it follows naturally from the black hole description, and the 10D black hole matches the 2D calculation for the classical action and the set of saddles. So this would be great to understand. temperature-dependent index. Yeah, so I alluded that there's a 10D solution that's causes a complex metric. So if the index is temperature dependent or the elliptic genus is temperature dependent, that means that the on-shell action will not be holomorphic in tau. So we have tau and tau bar. So this is the whole thing. I'll have to just write through it. But we also get temperature dependent killing spinners. So you can solve the type 2b killing spinner equation. So this is a 10-dimensional killing spinner in terms of some constants. And these killing spinners, because they depend on R plus and R minus, these killing spinners are explicitly temperature dependent. But they're smooth everywhere in the bulk. And it has the right number to match the number preserved by the elliptic genus. So this is really a whole nother talk. This one slide could have been a whole second talk, just doing the 10D calculation carefully and showing that it reproduces the JT answer. But we'll have to be satisfied with this. Okay, so discussion. So we sort of said that, if we take this near extreme limit, we could compute one-loop determinants. And those one-loop determinants already give you very different answers from what Hawking got, but everything that we've ever gotten, when we compare with the string theory results, when the comparison is justified, we get the right, we get the right things, at least at large N. And so with large amounts of SUSY, the path integral has this fine-grained information. And we can really classify different types of black holes based on which ones can appear as ground, supersymmetric black holes we can classify based on which ones appear as ground states in this setup. And so even if we only care about things like the elliptic genus, we still get very new predictions, which we haven't, we don't know how to derive them from a microscopic CFT. So this is a case where the gravity calculation is the state of the art, and the CFT calculation is now lagging behind. So if we had a CFT, we could try to probe different questions. Like, for instance, the BPS chaos question. Now, BPS chaos as an idea was the idea that even BPS states obey random matrix statistics, and we have to sort of define what that means. But now I'm saying that there are super selection sectors at BPS states. So they're going to inevitably obey a much more complicated random matrix type theory. And I have it under good authority that Clifford Johnson is working on the random matrix theory for large n equals 4, but it hasn't appeared yet. So we'll see when that appears. And so maybe there's BPS chaos and random matrix theory of a very rich form. And then also, if we had a weakly interacting dual CFT, we could think about this, the black hole cohomologies and the fortuity phenomena. So these very erratic jumps in the BPS state seems like they would be very interesting to understand from this cohomology point of view, because it means that there could be fortuitous and non-fortuitous states that appear and disappear as we vary some parameter of the symmetry algebra. And then from the point of view of microstate geometries, can we find some BPS solutions with the Ramon boundary conditions, which reproduce this? Maybe this is difficult, the Ramon boundary condition, but can you reproduce these even the nonlinear charge constraint from some kinds of microstate geometries? That would be very interesting. And certainly this temperature dependent index, if we had a way, again, this is all SUSY, right? This is all SUSY boundary conditions. So reproducing a temperature dependent index with a bunch of exact supersymmetric solutions that shows this jumping in alpha, that would be very interesting. So I'd like to stop it here now. This is my discussion. Thank you for letting me go well over time. I'm sure everyone is really pooped out and didn't follow the last half of the talk, but I'm really happy to answer questions after Raphael goes. I can remain on Zoom if people want to ask more, but I'll stop myself here, even though there was actually bonus slides about M theory. So I'll stop here for now, and thank you for your generous allotment of time.
So can I ask?
Yes.
Do just a second. So maybe what we can do here, we can have like a few minutes of questions, and then at 6:25, at 5:25. So in 7 minutes from now, we can go for coffee, and then we can have Raphael's talk. Is it okay? 5:25.
When's Raphael going to start?
Sorry.
When is Raphael going to start?
Oh, he can start at 5:25. So 10 minutes from now.
10 minutes. Okay.
Or 7 minutes from now. Is it okay? People can ask more questions. I mean, we can have more questions. Yeah. So it's in 7 minutes from now. You can have more discussion on Zoom if you want, and people want to have the discussion. But I think we're also doing some coffee. So 5:25 sharp we begin Raphael's talk. It's all recorded, so don't say anything bad about Trump because it goes on YouTube. So.
Yeah, not saying anything. Don't worry. Sorry, I was gonna make a joke, but it's being recorded, so let me not. Emil, you had a question, maybe just a couple questions, so I can give you guys a break because I know this is probably exhausting.
So this temperature dependence.
Yes.
Is this some sort of bulk indicator of Mach modularity of the index?
Oh, okay. That's okay. so my interpretation is that this factor that the temperature multiplies. So the index is a sum over different charge sectors, right? So first of all, we don't have a microscopic CFT, so I don't know if it's a Mach modular form or something like that, right?
But I was just wondering if you're saying it's like not holomorphic.
Yeah. So the complex solution, the on-shell action is non-holomorphic in tau.
Right.
Yeah, but that's the gravity solution. Whether the microscopic partition function has that property, I guess it sort of has to. It necessarily has to. Because I could write this beta as, T left plus, tau plus tau bar basically, right? So this, yeah, there's tau plus tau bar here, and so this is non-holomorphic. Yeah. But it's non-holomorphic in a very particular way because the tau plus tau bar, it multiplies exactly this right here. You can determine it from the algebra alone. So the idea is that the nonlinear superconformal algebra implies that there's sort of these different ground state energies. And the only non-holomorphicity is that the different BPS sectors, they can't all be zero energy. They have to repel each other in some sense. Yeah. So it's not a very radical temperature dependence. Think of this as a trace, right? This is trace of e to the minus beta h. And so what I'm saying is that h BPS is not always zero in this theory, that it's a nonlinear function of J. Yeah.
Oh, yeah. Okay. Yeah.
So given what I already told you about the BPS states, this is the only beta dependence that I gave you evidence for, and it turns out to be the.
Yeah, no, it's much more banal than what I was thinking.
It's banal in that sense. Is that there are a bunch of ground states, and they satisfy SUSY, but they don't all have the same energy that you compute from the Hamiltonian. Yeah. It'd be great to understand it though from the CFT side.
Emil, I had a question about your spectral flow. So if you begin with the NS vacuum,
yeah,
you do a spectral flow in your funny with the right type of a spectral flow. Do you get this relation between charges and angular momenta, which Matthew?
Okay. Yeah. So we did not spectral flow with the half integer spectral flow from the NS sector to the R sector. The way that we got to the R sector, or sort of an alternate way of deriving these one loop determinants, is by studying the NS sector partition function. You study the Virasoro character in the NS sector, and then do a modular transformation. So that puts you in the R sector, and then you expand at low temperatures, and you will get exactly these one loop determinants. So that's using the 2D Virasoro character. What we did not do was we were not able to spectral flow from the NS sector to the R sector with a half integer spectral flow. Basically, we got to the R sector from an S move, but not from spectral flow. And so I don't know how to do this more complicated half integer spectral flow in this theory. That's a very natural question though. That's something that we could have tried to consider, but we did not do it. So I wouldn't know how to get this kind of prediction. I wouldn't know how to get this from spectral flow. It's not even protected. Our conjecture is that this relation is quantum corrected to this relation. And this relation is pretty complicated. It's hard to see how you would get this from the NS sector, which satisfies J minus equals J plus. So spectral flow is an exact statement, but these relations, they receive quantum corrections. So that's why it's not clear if we should be able to match them.
In the large charge limit, again, if I'm in the bulk, I do in the large charge limit, spectral flow is just some coordinate transformation. So it's going to be some mixing up of the ADS Y and the sphere, the psi of one of the spheres and the psi of the other sphere. But Emil was saying that one spectral flow is better than the other. I mean, in principle, I can mix as much psi 1 and psi 2 as I want. There's some special, because this relation, okay, quantum correcting or not, I mean, this relation tells me that if I take the NS vac, the just global ADS, and I do a spectral flow in some way, I'll get some solution which will have two angular momenta, the type you want.
Yeah, but that sounds like what you should be able to get. I agree with that, but we did not do that. So I can't tell you for sure that that's what you should get.
It was a question mainly to Emil, if you have any, I mean, if your spectral flow is choosing to mix up a right amount of J from one of the three spheres and some other amount of J from the other three sphere. Do you have
Off the top of my head,
Yeah.
I'd have to think about it.
Yeah. Remember that he wrote the paper 20 years ago, guys. It was 2004. It was a different time, you know. And we
when
didn't
I had
have
more brain
the
cells, yes.
Yeah, well, no, that's not what I was implying. No, no. What I was implying is that sometimes the culture changes a little bit, and one of the main conclusions of the paper was that there wasn't a clear CFT where you could test these ideas, like just test the spectral flow, see the partition function reorganize itself. That's something that we're missing. So I tested the things that I understood in gravity from the gravity point of view. Though you're right that probably at large charges we could have done a diffeomorphism on this solution, but you know,
just put global ADS there and do a diffeomorphism, and you'll get some angular momentum. But you need to put global ADS. You don't need to put the black holes. If you just put global,
yeah. You could remove everything by diffeomorphism and just turn this back into the empty ADS metric, but then all the fields get twisted by these complicated twisted boundary conditions.
Sure, that gives you supertubes. That would be exactly that would give you the equivalent of supertubes in this background.
I see. Okay. So then, but if I did a diffeomorphism and turn this into empty ADS3, then it doesn't look like I should get this kind of relation, right?
The point is,
relation came from using the black hole solution.
Indeed, but the point is, if you take empty ADS, which doesn't have any angular momenta, and then you're doing a spectral flow on one of the spheres, you get the J minus. And then if you do a spectral flow with another parameter on the other sphere, you get the J plus.
Yes. Okay.
There's one wholly spectral flow, which is a combination of the two spectral flows, which is better than the other ones, which is the spectral flow of the theory. If you apply this, wholly spectral flow, which is the fancy one, do you get your J plus and J minus to be exactly the one which your relationship gives?
Well, if we did that, I would have put it in the slide. So we didn't try that. Sounds like a good suggestion. It's probably a relatively quick calculation. So
it's a very quick calculation. It's just that the solution you'll get will look like a supertube. So talking about microstate geometries.
Yes.
You'll have a supertube on one sphere and a supertube on some other sphere. So you get two big fat spinning guys. And if I can get solutions with those, those would be good solutions.
Okay. So you're saying that maybe, based on what you just told me, the answer to this question here is, from the microstate geometry point of view, maybe using this spectral flow idea with the supertube solution, maybe you could reproduce the semi-classical answer. I think that's plausible sounding. The exact one with the discrete jumps, or exact in the 2D sense, with discrete jumps, that sounds more difficult to get that. But at least the semi-classical one should be possible. Yeah.
The to be Raman ground states. So
yes, exactly.
We are very, very far away from the BPS. Then you have to do extra garbage to get to the gap.
Okay.
But just to get a angular momentum. But in principle, I could do a spectral flow on one sphere and another one on the other sphere. I can get two supertubes. I'm a bit confused. Why would you get these things with J1 with this particular relation? Maybe there's something technically wrong.
So this one thing I do, this relation, even the semi-classical one, it came because one condition, the BPS condition, this is the classical BPS condition. So this is uncontroversial. If you have killing spinners and supergravity, you'll get something like this. This extremality condition, this is like, the solution is smooth at the horizon. So this is the one that is usually the kind of nonlinear one that's the hallmark of the black hole. And it's only the intersection of these two that reproduces this relation. So I guess I'm going back and forth on whether if you got this kind of relation, it would have to be through a different mechanism than because you have a Euclidean horizon, right?
No, it's not Euclidean horizon. You start from global ADS.
Yeah, that's what I mean. Yeah. What I mean.
And you get the solution. So it's just that naively I would say if I do a spectral flow, I'll get any J plus and any J minus. There's no reason why. And because I start from a supersymmetric solution, I'm changing coordinates. What's wrong about the other solution?
Yes.
Maybe killing spinners don't have the right periodicities, but otherwise you have the solution.
Yeah, I think the killing spinners need to be smooth everywhere in the geometry for this BPS condition to actually make sense, right? BPS is not just that the charges satisfy this, but that the spinner is smooth. Did I give you guys time for coffee?
We got coffee while we were discussing, so I think.
Oh, I see. Okay. You guys are taking turns. Okay, that's good. That's good. I'm just gonna flash this slide up here. So there's also ADS2 cross S2 cross S2 cross T5, and we believe our results apply to this case of 6 intersecting 5 branes. So this might be relevant for the M-theory solutions that you have in mind as a different example that has n equals 4 superconformal symmetry. So I'll just flash that up there, and hopefully we can talk later. So thank you for giving me like the monstrous amount of time you did. I hope this was interesting, and the suggestion with the spectral flow is a great one. That's something that we can try soon, actually. But perhaps I'll stop here and allow the next speaker to go.
Can you put that slide back up again for a second? Matt, can you put the slide back up for a second?
Oh, I'm sorry. Yes. This slide. Oh, sorry. You don't see it, so you don't know. Share. Share. And to be clear, this is from Boonstra Scandaris. Oh no. Oh, sorry. Okay. We got the whole talk. I would have finished on time if I went through my slides this fast, you know?
It's 9.
Yeah,
Okay, you wanted this one right here. So this solution was in Boonstra Scandaris, and co. From 1998, but we kind of decided to redo it because 1998 is a little while ago. So, and I've seen almost no one talk about this ADS2 cross S2 cross S2 cross T5, but the configuration of two branes and 5 branes is probably of interest to you guys. And so this is a solution of 11-dimensional supergravity, and you can compute S naught and alpha in it. But we were not able to compute the Schwarzian coupling because we don't have the non-extreme version of this black hole. That would be interesting to figure out what the non-extreme solution is. So, okay, you got the picture, you got the slides. I'm off the hook now.
Thanks. Okay, so we'll begin the second talk of this.
Thank you, guys.
Evening. We are very happy to have Raphaël Dulac, who will be telling us about ADS solutions and spikes. Hopefully there will be a link. Maybe we'll find some microscopic versions of that. I'll close.
I cannot speak about that.
Oh. Make it small and then share it.
Okay. I think it's all good. So, can you hear me well?
Online, can people hear?
Yes.
Okay. So first of all, thanks to the organizer for the opportunity to talk. And so I'm going to mostly talk about the paper which will soon appear with Josip Vena, Antoine Bourget, Dimitrios Soulikas, and Nick Warner, so all the Sackley team. Hopefully I made the talk, I think, the less technical as possible. So if people are not too tired, I think it will be kind of possible to follow. So as you know, like one of the main goals and the main interest is to capture the microscopic structure of D3D5P black holes and 2M5P black holes, or to explain the entropy of black holes. So on earlier work with Josip, Sumangsu, Anthony Hoop, and Dimitrios and Nick Warner, we made already some work on the M-theory case and on the possibility to add some momentum to some intersecting brane systems and some fractionating brane systems. So in all talk, I will not talk about the M2M5 case, even though it's the one which is the most related to what Matt told us, but I will rather focus on like this D3D5 NS5 thing, NFI branes. So, okay, why did I focus on this one rather than the other one? It's basically like the integrability of structure is like more under control and it's kind of easier to handle. And it's probably due to the fact that those ones are some known CFT dual, because they will have some ADS space which will be around, and the CFT duals are known. They are like either Gayuto-Witten boundary CFTs of n equal 4 Supergravity mills, or there are like 3D n equal 4 gauge theories, SCSs. So we'll have like these three branes, NS5 branes and D5 branes. So they will all share like three common directions, which are x0, x1, and x2. The D3 brane will be extended along the Z direction, which is D3 brane direction, and the D5 brane, which will be in flat space along an R3 transverse to the D3 brane, and the NS5 brane will be on another R3 that will be called the V space. So this setup was introduced first by Anani and Witten to explain mirror symmetry in string theory, and yeah. So that's what I will talk about. So the first thing to do, and that's what Lunin did in 2007, is to write the most general intersection of D3, D5, and NS5 branes. So yeah, just to recall, I put it like where each kind of branes are, and so that's the most general ansatz. So here we can see like the three directions. Maybe I should point with. Okay, I don't have any mouse. So like dt, dx1, and dx2 are like the three common directions to all the branes, and that's basically the directions on which kind of most things will happen. Then we have the u-plane with a wrap factor, which is exactly the one for d5 brane, and then s5 brane along the v direction, and then we have z. The z direction is the d3 brane one, and it has some fibration along the u-plane. So the fibration is because the branes in flat space, the D3, the D5, and the NS5 with those positions are really the brane flat space position. But it's well known that when branes are ending on other ones, they bend the other one, and then they okay. And yeah, and then they bend. So basically, the D3 brane, so which is along the Z direction, will bend the D5 brane, which is along the U direction. So some things you may want to ask. Oh, first of all, okay, there are like some gauge field, which is like D5 brane with a C2, B2, it corresponds to NS5 branes, and then the D3 branes gauge. So basically, that's the most general ansatz, which determines the most general intersection of D3, D5, and NS5 branes. One question you might want to ask is, why is the fibration along the U direction? It seems not very democratic, since you could also have the same thing with V coordinates, but actually that's really a coordinate artifact. You could also have a fibration along the V coordinates, but by doing so, you need to have to use this coordinate z as a function, and w becomes the variable, and so you exchange the role of w and z, and it will exchange for you the role of u and v in exactly the same way. So as you can see, this solution, which is like the most general supersymmetric intersection that you can have, is controlled only by two functions, which are a0, which appear as a wrap factor, and it appears at several other places, and then the w function. So all of them are governed by pre-potential G0, which has to satisfy Monge-Ampère equation. So Monge-Ampère equation is this, okay, rather, it might seem simple, but it's very hard to solve. It's non-linear, and so LV is the Laplacian on the R3 parameterized by the V coordinate. L of U is the R3 parameterized by on the R3 is a Laplacian on the R3 of the U coordinate, and then you have a bunch of derivatives. So yeah, this is a very hard equation to solve in general, and rest of the talk will mainly be to try to have solutions of these kind of things. And yeah, so one question is, can we find solutions? So first of all, we have the general ansatz with U, V, and Z, which could be whatever they want. So we will impose spherical symmetry on the two R3 parameterized by the U and the V directions. So it physically corresponds to intersections of D3, D5, and NS5, and the D3 will end in a, and you will assume some spherical symmetry on the intersection between the D3 and V. The other thing that we will do is to impose some scaling similarities. So basically, it will be we have a 3-variable problem, which is very hard to solve. And what we'll do is impose this scaling symmetry. So U and V will both scale with mu, which will be a scale, and Z and W will scale as 1 over mu. So the first thing is we'll explain why the scaling similarity in particular, and then we will see that, okay, we can generate a whole bunch of solutions, and basically Docker did it for us, and we do a mapping from a set of solutions to a set of other solutions. So, okay. So we'll see that the descaling, and we'll try to explain where is it coming from. So we derived the ansatz by Lunin, which was like very adapted to branes in flat space. So basically, you know the branes, you know like the physics is, okay, let's say rather simple to read, but you have to solve a horrible Monge-Ampère equation that you are actually not really able to solve unless for clean D5 branes or like just a D3 brane for like the very trivial cases. On the other hand, Docker and collaborator also on their type 2B paper, it's with Estes and Goodpearl, they showed that you have an integrable structure for the intersection of D3, D5, and NS5, but it involves some ADS space. So ADS space, we will write it in Poincaré coordinates. Poincaré coordinate because when you take the near horizon of some near brane limit of some branes, that's what appears, and you have a nice scaling similarities. So yeah, the brane physics is rather obscure in this setup, and that's why we try to elucidate, but you have an integrable structure, which is what you want. So first of all, you can ask, okay, you cannot really see, but why they are scaling? That's basically the question.
On Zoom, I see.
Oh, on Zoom, they can
on Zoom, I see. On Zoom, I see, don't worry.
Okay. So okay, to have some intuition about why is there scaling, we'll use some probe D5 and D3 branes. So as I told you, and as Callan and Maldacena first showed, at the probe level, when the D3 branes and on the D5 branes in a spherically symmetric way, the D3 branes tend to pull the D5. And then you have some profile, which is an harmonic one. So basically, Z is a scalar field now from the world volume of the D5, and it has to be harmonic in the 3-dimensional plane. So this is why it has to be 1 over U. Of course, there are also some gauge field from the world volume of the D5 brane, which just source for you the D3 branes. But okay, let's just be simple and focus on the scalar field. Okay, it's not very hard to have like the gauge fields too, but that's what we want. Okay, so we have a profile Z of U, and we have a charge in front of it. So it's basically telling you that the pooling of the brane is controlled by QD3, so the number of D3 branes ending on the number of D5 branes, and it's basically the ratio which controls that. So basically, it's a BPS solution to Born-Infeld action. It's also a solution to the linear electromagnetism equation with the same U1 fields and everything. So it's also a solution of the maximal supersymmetric solution on world volume of a D5 brane. So on world volume of a D5 brane, you have if you have a UN maximal supersymmetric theory in 5 plus 1 dimensions, you have a bunch of operators, and basically you can find a solution on which on each of the diagonal components you have a different spike. So you have the scalar field are in the adjoint representation, and then you can just on each of the diagonal components of the UN gauge group have different spikes. And you can put different strengths, and it's still BPS, and it's still a perfectly fine equation of motion. So basically what you start to see is that you have a structure on which you can have several spikes, and for which the strength of the spike will govern for you the you increase the charge, and you are moving in this direction. So
Raphaël, can I ask a question?
Yeah, sure.
Is there some strong curvature or large string gradients of the target space near the spike?
so at this point, it's only at the probe level, right? So you don't have to really care about these kind of things. But okay, for the validity of the solution, basically you could say that near the z goes to up the spike, you could say that the solution fails because you have like from the point of view of the world volume of the D5, you have some sort of singularity. But that's just a fake thing, and basically you have infinite energy, but that's just because you have a semi-infinite disturbed brain. Does it answer the question?
Yes.
Okay. So yeah, the hint of this thing is to use z times u as a coordinate because it's scaling the right way, right? So basically, if u scales with mu and z scales like some charge, which you will use as a coordinate along this space, yeah, this is the intuition of what will give rise to the ADS4. So yeah, let's move on. And so basically, this was for D3 and D5. You could do exactly the same thing for D3 ending on NS5. It's still harmonic. It's still very fine. It's still perfectly fine. And you obtain the same kind of behavior for V and W, which has to scale in opposite way. So that's why you can use this ansatz. And actually, we'll see from the type 2B case that these things really mean that you have a D5 brain. So here you have some D5 source, and you have either you have a spiky region and with a strip, and at one side you have ADS4 cross B6, and at the other one you have ADS5 cross S5. So at this point, it might seem a bit okay. Maybe you don't fully understand, but it's first to give you a kind of picture of what will happen when you will have the full solution, because it's okay. I spoiled the result so that you get less lost after. So here you are sort of zooming in different regions of these intersections depending on where you are on the strip. So for example, you can see that if you have some ADS5 cross S5 region, it means that you are zooming on some district brains, right? Because the near brain limit of a bunch of clean district brains is ADS5 cross S5. So now let us write the most general type 2B solution. Okay, at this point, if there are questions about the M-theory case, I can also comment on it because it's ADS3 cross S3 cross S3 cross some Riemann surface. But here, what we have is that we have an ADS4 space and two S2s. So the S2s are really coming from the same S2s of the spherical symmetric ansatz in the brain flat space limit. So you have two S2s and one ADS4, which are wrapped over a Riemann surface. So you have the full Riemann surface on which, okay, everything will depend on. So basically F4, F1, F2, and all the gauge fields. So will depend. And yeah, you just fiber it, fiber the space of ADS4 times S2 times S2. So what are you allowed to do with those things? First of all, you are allowed. Okay. First of all, you are allowed to have a different topology. So you have you have a strip, which is a Riemann surface over which everything is fibered. So you have to impose some boundary conditions. So the boundary conditions at the two ends of the strip will basically tell you whether you have some district brains asymptotically or not. So you either have like two ADS5 at the two ends of the strip. It will mean that you will have really some district brains which will go all the way through the geometry. So it's not like the spike you saw before, where the district brain when ending on the D5, you could really have like some district brains in all the geometry. You can also have ADS4 cross B6 and ADS5 cross S5, which means that no, it's the one. Yeah, thanks. So this thing is really it's the sort of it's the spike that we saw before, because we only have one ADS5 regions, which means we only have some district brain which can escape in one direction. And yeah, And we have ADS4 cross B6 because the space smoothly cap at some point. And then you can also have a ADS4 cross B6 times and ADS4 cross B6 at the two ends. And this one is rather, okay, it's a bit more mysterious because you don't have any asymptotic disturbances, but we will come back to it later and explain in great detail what it is. So what we want to do is basically to have a map between the two solutions and to really explain what's the brain and what's the physics of this ADS4 cross S2 cross S2 cross the Riemann surface solutions, on this side you have the integrable structure, and on this side you have the things which are adapted to brain and cluster. So, okay. So here is the ansatz, and basically the ansatz is, okay, it's a very, very nice solution because everything is only governed by two functions which have to be harmonic on the Riemann surface. So you have a Riemann surface, you just have to give me some two harmonic functions on this Riemann surface, which has, okay, H1 has to vanish at the upper part of the strip, and sorry, H2 has to vanish at the upper part of the strip, and H1 has to vanish at the lower part of the strip, and you can have a bunch of poles. So what will be the pole? The pole of H1 will correspond to D5 brane, which are like the blue dots, and the poles of H2 will correspond to NS5 branes, which are the red dots. So you also have to introduce the the harmonic dual the dual harmonic one forms, the dual harmonic functions, which are these H1D and H2D. So they do not correspond to new data, so it's perfectly fine. You really just have to give H1 and H2, and you will obtain the full solution. And okay, you just choose the number of poles. For example, if you have two poles in H1, it will mean that you will have two D5 branes. And then it fully determines all the solution for you. So because H2 is shrinking on the upper part of the strip, it means that on the upper part of the strip, one of the two spheres will shrink. So if one of the two spheres shrinks, you can integrate the three form you have a three cycle over you have a three cycle, which because you have like two spheres which shrink at the two ends, and then C2, which is represented here, is a three cycle along which you can integrate the three form field strength so that you obtain the number of D5 brane. So this is a computation you can do, and you can do the same thing for the with the NS5 field strength, and you obtain the number of NS5 brane that you have. So because on the lower part of the strip, now S1, which is shrinking, and so that's the one which will give you the free cycle, and you integrate over C1, and you obtain the charge. So now you may ask, okay, I talked about the D5 and the NS5 branes, so the 5 branes, but there are also some okay, here there is typo. I want to talk about 3 branch charges now, and 3 branch charges you need a 5 cycle. So yeah, because you want to basically integrate F5 so that you get the number of these 4 branes. Actually, here there is some subtleties about how to compute the charges because of the Chern-Simons interaction. So because of the Chern-Simons interaction, basically D of F5 is not 0. So it's not a conserved charge. So because it's not a conserved charge, that's probably not the thing you want to integrate over. And indeed, you have to introduce the paid charge, which is localized and quantized, but has some other problem that it's not gauge invariant. And that's the thing we will ultimately integrate. So okay, I don't give too much details, but that's really what you want to integrate. So what are the 5 cycles in this geometry? So there are 2 kinds of 5 cycles. First of all, we had 3 cycles before, and we have big spheres. So to have a 5 cycle, you can take a 3 cycle, and you fiber the other sphere, which is the one which is not shrinking, and it gives you a nice and clean phi cycle. So basically, at the top of the strip, S2 was shrinking, and then S1 is perfectly well behaved, so that this cycle, it's really a phi cycle because S1 does not have any problem. What does it mean? It means that on the upper part of the strip, we should integrate QPH1 because this is the one which is well defined. Indeed, C2 was along, okay, there is, okay, oh, sorry. That's, you want to integrate QPH3 on the upper part of the strip. Why? Because C2 is the cycle, like, which is well defined, and basically B2, so B2 was the, okay, NSNS B field is proportional to the volume of the S1, and basically this is the one which is well defined on the upper part of the strip, and then you should use this this phase charge because this is the one in which you can really integrate and which is well defined. On the lower part of the strip, it's the opposite, and the thing you have to compute, and the thing which is well defined is rather the other one. So basically, now the story is opposite. S1 is shrinking, so you have to integrate over a sphere which remains big and which is not shrinking, and that's S2. So that's what you should integrate this thing. So another thing okay, those are the 5 cycles on which you can integrate the branes, but they are not really 5 spheres. So they are topologically S5 5 cycles, but they are not 5 spheres. On the other side, you can also integrate because here on the upper part of the strip, S1 is shrinking, on the lower part, S2 is shrinking, and then topologically, this line corresponds to 5 sphere on which you can also integrate the class. But it will not play a role unless when you want to measure, for example, asymptotically, if you have ADS5 cross S5, you have an S5, because here you have a non-trivial and non-contractible 5 cycle, which comes from here, from the upper part of the strip down to the lower part. Yeah. And so basically, the formula are rather nice. And for example, something which will be important and we will study a lot is basically on the right-hand side of this equation, you can see that QD3 page 2 over QD5 is just given by the harmonic dual of H2 evaluated at x0 plus I pi, where x0 is basically the position of the source of the D5 brane. Okay, nice. Is there some question at this point, or? Happy so far. Okay, so you can do the mapping. So it's a rather okay, it's a lengthy computation, but with a very short answer. So you want to basically find the u, v, z coordinates as function of the coordinates on the Riemann surface. So in particular, everything will depend on the scale of ADS4 and on the coordinates which are on the Riemann surface that we call x and y, or xi and xi bar, which is xi is just equal to x plus iy. So okay, you do the mapping and you obtain this rather simple expression where h1, h2, h2d, and h1d are just the harmonic function that we had to interpret before. So we had a mess. So f4, f1, f2 are a very complicated function of h1, h2, and their derivatives. But at the end of the day, u, v, z, and w are very simple expressions. And okay, we'll try to give so yeah, we mapped it, and we'll try to give like some physics intuition behind all of this.
Sorry, Raphaël, can you repeat what are the definitions for, or what is the meaning for the charge, the D3 page charge, the two different D3 page charge?
Yeah, sorry. Yeah, so basically, if I write thing on the blackboard, can you see, or?
Probably not. No, but just is the first one somehow like the D3 charge diluted in the D5s and the second one diluted in the NS5s, or is it something like that, or can I understand?
There are some D3 brain charge which are induced by the Chern-Simons interaction. Like even if you don't have like properly D3 brain sources, because dF5 is equal to F3 wedge H3, you still have like some charges which are induced by the D5 and NS5 brain charge. And then the question is, how can you integrate them? And to integrate them, you should just integrate the one which is well defined. So
and do you have a third D3 charge, because you're in the last picture you have this S5, so I wanted to know.
Yeah, so basically here you can compute, but you can see that this S5 you can deform it in order to measure, like it will be not, yeah, you can deform it like what Joseph is showing, so that yeah, take the red one, the last one that Joseph drew. Basically you can see that it will mean that this charge will exactly be given by the one which is asymptotically, so on the ADS5 process 5 regions. No, here, if you can draw something here. Oh, it's here minus here. So
the blue guy minus the red guy.
Yeah, exactly. So it's the blue guy minus the red guy will give you the one which is given here. So on the blue guy, you're really integrating F5 because it's a sort of ADS5 process 5 region, and you have to subtract the thing.
Sorry, you said blue guy minus red guy gives you the guy which is here and that did not get the here.
Plus, depends.
Yeah, or plus. It depends on the orientation, but it gives you the one on the that you would integrate in following the black S5.
Uh-huh. Okay, thank you.
So
yes, I'll erase those things.
Okay.
I think I will have a question for Joseph at the end of the talk. So yeah.
Don't worry.
So
go ahead.
No, you can ask it now.
Maybe later.
Let's go later. Okay. So I just want to refine a bit the structure because having H2D or H1D much seems a bit mysterious, and the proper way to think about it is that Z is basically 1 over U. So 1 over U should recall you really like the probe D3, D5 spike, or the same for V. W is 1 over V times something. And this something is basically the cohomological part of the gauge field, which is the things which once integrated, like this is the one which is non-smooth. And this is really the one which once integrated would give you the D5 or the NS5 sources. So that's part of the structure because that's really what connects to the M theory case. So in M theory case, you had like an M2 ending on an M5. So it's Z is equal to 1 over U squared because now you are harmonic in 4 dimensions. But the factor which is on top of it is still the cohomological part of the gauge field. And that's something which is rather important in the structure of all those equations. So now you can ask some questions. Why did we do that? We want to have like a nice structure of understanding the brain structure of all these ADS4 solutions. But for example, you can ask, can I have a clean probe D3 brains in these ADS4 solutions? So from the ADS4 solutions, it's rather mysterious and it might seem to be a bit hard. But but since we have the mapping, we just know that the Coulomb branch should be just a D3 brains along the Z directions and along the three common directions of all the other one. So basically, you can expect the D3 brains to just be from this picture. It has to be a constant in the R3, in the two R3s corresponding to the V and the U space. So it should be U is equal to constant and V is equal to const. And indeed, that's you can solve the equation of motion and you identify the D3 brain, which really corresponds to identify the Coulomb branch for the D3 brain in this picture. So it's but you can see that from the M theory, sorry,
D3, right? It's a D5.
Where? Oh no, so sorry. The D5 is correspond to the blue dot. Here, in black, it's in black, it's the D3 brane, and here it's the D5, and here it's the NS5. And basically you can, okay, this is a drawing which is schematic. It's not the real curve, but you have to solve for 2 mu times h1 is equal to a constant, and 2 mu times h2 is equal to a constant. So that's a rather simple curve, and basically it corresponds to identify this region. So you can see that the D3 branes will reach mu is equal to 0 in the ADS5 process 5. Like if you have an ADS5 process 5 asymptotics, the D3 brane will escape and will take value mu is equal to 0 in this direction, which is okay. It just perfectly makes sense. You are inside the ADS, you are very happy, and you are on the, you just become parallel to a bunch of ADS5 process 5. Yeah, a bunch of other D3 branes, so just clean thing. But on the other side, here you can see that when you have ADS4 cross B6, mu is going to infinity because you are leaving the ADS space. Mu goes to infinity is really like it hates ADS and it tries to escape. So that's okay. That's something which we learn from this thing. The other interesting probe are like D3, D5 spike in ADS4. So what are D3, D5 spike? So, okay, you have D3 and D5 brane charge, and something we said in the probe in flat space computation that everything was governed by an harmonic function, which was governed by the ratio between QD3 and QD5. So basically, to know where does the probe D3, D5 will sit, you just have to solve this rather simple equation. So the harmonic dual of H2, you have to solve for x0, like the position on the upper part of the strip. H2D has to be equal to QD3 over QD5. So it's really a point in the Riemann surface. So you really just need to identify a point, and then the D3 brane will perfectly sit in the ADS4 process 2, cross the, okay, just one of the, so ADS4 cross S2. And it really means that this mu coordinate is really a coordinate along the brane, because it's just a point in the Riemann surface, you have a point in the one of the S2, and then you just fill the full ADS and the S2. So it really means that this probe, this D3 spike, so all those geometries are made of spikes. But that's not so surprising, as we said before, at least in this case. So now we'll reverse the thinking. So before we had a probe, and we said, okay, I want to have a probe. I have QD3 over QD5. I fix it, and it gives me a position. But now, to think about what is this coordinate, what's moving in x0 mean, you should really think the other way around. So it's more like QD3 over QD5 is a coordinate, and basically moving along QD3 or QD5 is basically moving along the strength of the spike. So we are sitting at v is equal to 0, where we have the D5 brane charge, and really moving along the upper part of the strip means that you are moving along x0, and moving along x0 means that you are moving along h2d of x0 plus I power over 2, which is an increasing function of x0. So it just means that this coordinate is very simple, and it just going up in the increasing the strength of the spike. So okay, we'll conclude. Okay, the same story holds for D5, NS5 and D3 spikes. So you will go to the other patch. So basically you would go to V is equal to 0. So V is equal to 0 corresponds to the, to U is equal to 0. So it corresponds to go to on the lower part of the strip. And then you would have spikes in the VW plane, and the same structure holds, and it's quite universal. So so we conclude that all we see are spikes, and nice and happy spikes. So in particular, if you have two ADS5 region, as I told you before, it means that you have these 3 branes which escape to the 2 infinities. So you have 2 ADS5 regions on which you have like a clean 5 cycle, and on which you can really integrate this 3 brane charge. And then you have spikes, all of them end at the same point. So, okay, this picture is rather clear, and that's the same when you have one ADS4, so you have an end on the strip, one ADS4 cross B6 at one end, and one ADS5 cross S5 at the other end. So all of them are also just a bunch of D5 and D3 spikes, or a bunch of NS5 and D3 branes. So basically, you just have to choose the D3 brane will end, and like all the asymptotic D3 branes will end either on the D5 or on the NS5. So yeah, that's okay. That's just all spikes. But okay, here comes a puzzle. When you don't have any ADS5, you don't have any asymptotic D3 branes yet. So what does it even mean to have what does it even mean to have a spike? Yeah, because okay, where are you zooming on, and why do you have a spiky structure? So okay, that's what I will try to explain in the rest of the talk. So before doing that, let me move on. Some things I didn't know before this project is sometimes you have some systems who preserve edge supercharges, and even though they preserve edge supercharges, they repel each other. And that was quite surprising for me. And this is the case for D5 and NS5 branes. And for example, that's the same story for D0 and D8. They share some, it's an edge supercharge system, but the D0 branes is repelled by the D8 brane. And okay, you can see that from, okay. First, you can think of it as, say you have an NS5 brane background. So this is the metric of the NS5 brane, and you have an harmonic function. We use the U and Z coordinates, just adapted to what we had before. So the same U, Z, and V coordinates, and you can integrate it's not too hard. You can integrate the V field, and that's the metric of the NS5 brane. So the third thing you can think of is, you put an F1 parallel to the NS5. The F1 is, it's an edge supercharge system, and it's a floating brane. So as long as the F1 is parallel to the NS5, the F1 will just float. And end of the story. But when you have a D5 brane, even though it shares some supersymmetries, actually you can see that the profile is not at all. The profile is not at all trivial, and the brane is not floating. So what is going on? Actually, what's going on is that, as I told you, the D5 and the NS5 repel each other, and then you have a non-trivial structure. And in particular, you can see that, a first hint of having a scaling region is that if you send U to infinity and Z to 0, this thing will just go to pi over 2, and Z times U will just be a constant. So that's sort of a first hint that in some limit, these scaling regions, this region have some, these probes, so the 5 probe in the NS5 background have some profile and have some scaling regions on which maybe the ADS4 is living. So yeah, and that's indeed what is going on. And we'll see just a bit later. The last thing I want to mention is that Z times U seems to recall to us that it's a spiky region, and basically it's indeed a spiky region with some discrete brane charge which are induced on the word volume of the D5. And indeed, that's really what's going on. You have some discrete branes which are on top of the D5. And another way to say it is because of the Chern-Simons interaction between the D5 and the NS5, even at the probe level, you have some discrete brane densities which are here. Okay, so actually the full story is a bit more complicated since you have to backtrack everything, but you can still, given that you have n NS5 branes and n D5 branes, so in red you have the NS5 and in blue you have the D5, and you have some scaling regions which correspond to z goes to 0 and u goes to infinity, and you see that you can measure some induced flux. And the D3 flux is really n NS5 times n D5 over 2. If you don't have any D3 brane stretch between the D5 and the NS5. But you can also have some D3 brane stretch between the NS5 and the D5 in general, because it's just what Anani and Witten told us, that you can have some D3 brane stretch between them. And in particular, the maximal number of D3 brane which can be stretched between a D5 and an NS5 is the product of the number of NS5 and number of D5. That's what is usually called the S rule from field theory best practice. And then you can ask, okay, in this case where you have the maximal number of D3 brane which are stretched between each other, what's the D3 flux which lives on the world volume of the D5? And actually, this flux is minus the number of D5 branes times the number of NS5 branes over 2. And okay, so that's basically what all our geometries are. So all our geometries, they correspond to zoom in on these regions, which, okay, naively might seem to be far away from the, yeah. So basically what we are doing is the ADS4 correspond to zoom in on some spiky region. What we have is we identified some spiky regions, and we have some ratio of charges, which is the things on which you zoom, so that you, which knows about all the physics of the system, and basically that's taking, okay. So, this is where like the ADS4 scaling region is coming from. It's okay. It might seem a bit strange. Why? Because okay, we know that the ADS4, in this case, we don't have any ADS5 regions, and these ADS4 are known to be the dual of some 3D n=4 SCFTs, and in particular to gauge theories, to quiver gauge theories, and which flows in the IR to those 3D n=4 SCFTs. But naively, you might say, okay, what's the IR limit? The IR limit would correspond to zoom on the D3 branes which are stretched between the NS5 and the D5, because the 3D really comes from the field theory living on the world volume of D3 branes once you took the IR limit. So once this region is sent to 0. So, but okay, actually, that what we learn is that that's not at all what's going on. What's going on is that we are zooming on some scaling region which are seemingly far away, but because we zoom in on these regions, it sends the two ends of the things to infinity, and it looks like some infinite spiky regions, and that's why we have two ADS4 cross B6 at the two ends. So there are no asymptotic difference, and the gravity theory, gravity solutions knows about that, but yeah, that's what we have. So another way to try to see it is so we try to show the fully backreacted D3-5 plane for the fully backreacted solution. So basically, this plane corresponds to the v is equal to 0 plane. So we are moving along this x direction because that's where v is equal to 0. And you have a bunch of spikes. So what you can plot is first, you can plot you have two D5. So you have two different spikes, and those two spikes are the black thing. So they are just u is equal to 1 over z is equal to 1 over u times the charge of D3. Okay, the second thing you can try to plot is basically u times z. we say that u times z coordinate is the thing which is measuring the strength of the spike. And that's exactly what it is. So basically u times z is this purple curve, which, yeah, this one. So is it purple? Yeah, blue. Okay, yeah, but gray. Not this blue. Blue gray. Blue gray. Okay. The blue gray one, and so it's really measure like the strength of the spike. So it's an increasing function, and that's also what you expect when you're moving along x0. You would say you would expect stronger and stronger spikes, and that's what you have. And the final thing you want to plot is u times z. And actually, u times z, the u of x, z of x in this plane. So those are like the red, blue, and green curves. So why did I draw 3 different things? Is because basically these things as functions are only well-defined and not going to infinity, only on subregions. Because whenever you will hit the fibrine, you will see that the curves will just go all the way to infinity. So it will correspond to the z goes to 0, u goes to infinity limit that we saw just before. And in between the 2 branes, so it's here, you have the blue region. So the blue region really like is another curve on which u and z are both finite and well-defined, and then you again hit a spike and you go all the way to infinity. Like u goes to infinity, u goes to infinity, z goes to 0 again, and then you hit one more time the green thing. And
so this curve is doing something like this, or it's at the origin?
No. Okay,
the blue curve.
The blue curve is just moving between the 2 blue dots. On the, yeah. So going from the left-hand side to here, to the first blue dot, it corresponds to the red curve. Then moving in between the 2 blue dots, it's the blue one. And then moving from the last blue one to up to infinity, it's the green one.
So the red one is here.
Yeah, exactly. Yeah.
Oh, okay. And the green one is the other one.
The green one is the other one. And then you can continue and yeah. Yes. So do I want to say? Yeah. So basically, and you can play exactly the same game in the NS5. Where v is equal to 0, u is equal to 0, and then you plot in the VW plane, and you have a bunch of NS5 branes. But now, because you have 3 red dots, you have 3 sources, and then you have 3 spikes, and you would have 3 black region, like black spikes. And that's the geometry of the thing. And so, okay, let me conclude by some general remarks about what we did and the future things we might want to do. So the Docker solution, we mapped the Docker solution to branes in flat space, and thanks to that we resolved the brane structure of the brane structure of those ADS4 geometries, which was quite obscure, and which, in order to build anything interesting for the Microstate geometry program, you really want to resolve. So that's what we did. Then we showed that I didn't really go deep into details, but all the ADS4 cross B6 solutions are the holographic dual of good 3D unequal force SCFTs, and they correspond to taking the higher limit of a bunch of NS5 and D5 branes with these 3 branes stretched between them. And we showed that, contrary to the naive thought of zooming on the D3 branes, on which the degrees of freedom of these SCFTs are, you zoom in on some scaling regions which might seem far from the branes, and basically all the regions of the D3 branes is squashed together so that it's become 0 size and you cannot see it. But then, here comes I don't know if it's bad news or good news, but that's not really the geometries you want to use for the Microstate geometry program, because those things are dual to SCFTs. Okay, either boundary conditions, 3D boundaries of n equal 4, or to 3D n equal 4 SCFT. But what we would like is really to have like more the dual of some confining theories on which you have just a bunch of D3 branes and D5 brane, and not the NS5, for example, but without any asymptotic D3 branes. But to engineer such a situation, you cannot have any ADS, and actually it's what we could call maximally bad in the sense of Guyot and Witten. So for example, the thing we would like to construct is the dual of the two Spolyakov monopoles, but it's yeah, that's not in this class of solution, and that's for future work what we want to do. So yeah, thanks for your time, and yeah. Is there any question?
Yeah, just a suggestion, again, linking it with Matt's talk. Matt was saying that, oh, it's very hard to get the CFT. It's very hard to get the CFT because you get this ADS times S times S. But now you're basically showing that this ADS times S structure comes not from branes. It actually comes from spikes.
Yeah.
So if you want to get the CFT, and if you look at just, stupid branes, which are flat D5s and flat D1s, the ones that give you the supergravity solution, by looking at their intersections, you'll never get the right CFT. Because they're not the fundamental objects. They're not the fundamental building blocks of the solution.
Yeah.
The fundamental building blocks of the solution of these solutions seem to be basically these spikes. They seem to be D3, D5 spikes in this particular case, and in the other, in Matt's example in M theory, they're going to be some D1, some F1 D5 spikes, or some F1 and some D5 prime spikes. The fundamental building blocks will be spikes. Will not be clean flat D branes. That's somehow what.
Yeah.
That seems to be the.
Can I comment on that, Joseph, just really quick? I don't know if that was actually a question, but I can make it a further elaboration on that. So in Emil's paper with Andy and Sergey and Greg Moore, they discuss 3 different ways of getting this ADS3 cross S3 cross S3 cross either S1 or R. So there's option 1 is the straight intersecting branes, and that doesn't give you the compact S1. Option 2 for them is the bent branes, and I'm trying to interpret their bent branes as these spike solutions. Is that correct or incorrect? Option 3 is the one I used in my talk, which is that there's one set of branes is dissolved into fluxes. But is option 2 with bending branes, are those the same as the spikes that appear in this talk?
I don't think so. No, nobody knew bending branes. Nobody knew about them until our paper last year. So I don't think anybody knew about bending branes. They're different. I mean,
Can Emil maybe make a comment? I don't know.
They're not bending branes.
To be honest, I don't know.
This is some case where you have branes that are like this, and then what happens is rather than them just being intersecting, it kind of dissolves into one set, and then this kind of shape. I mean, it's the same picture is drawn as what Raphael was drawing, but it might be that it's a different geometry. It's this picture of branes that do this, which is what I thought these spike solutions were. Maybe this is just my misunderstanding of the spike.
They're not doing. Their solutions are not any of that.
Okay, I see. Sorry for my misunderstanding.
That's coming from some sort of bending.
No, their solutions are. So that's the whole point. Those solutions are coming from flat infinite branes. And then that's how you get all this ADS cross S times S1. You basically put some flat infinite branes. But then there's a very weird thing that if you look at this flat infinite branes, and you want to get the spikes, for example, so if you get a spiky solution like the one Raphaël has, and then you smear it, you get a similar solution. So you get the same supergravity solution either by smearing infinite spikes or by smearing flat branes which are not intersecting.
Okay.
Which I don't think it was. I mean, I don't think it was realized. And I'm looking at the paper by Emil, and there's no mention of spikes. And in particular, the ADS coordinate it's a coordinate along a spike. That's the weird thing about the ADS coordinate.
Yeah.
A couple of comments. So the reason why the ADS emerges in this picture is because of the self-similarity of spikes. But one of the interesting things that may be a message for the CFT, I don't know. So here's the warning first. Everything here is based on non-compact Riemann surfaces.
Yeah, exactly. Yes, yes, yes.
The extent to which this survives a compact Riemann surface, I don't know. But one thing that sort of surprised us and is remarkable about the spikes is, as Raphaël was describing, the spikes have a steepness and they organize according to steepness. So if you have, let's say, 27 brains of D3s ending on three NS5s or something, it makes a spike. And then what happens is the steepness of the spike depends on how many D3s are ending on a particular D5. And suppose 9 end on the first one. That makes a very steep spike. And steep spike, maybe 25, 9, well, maybe another 12 end on another spike, maybe another 4 end on another one. They all have different steepnesses. And so the single intersection of D3s and D5s stratifies into a bunch of different spikes concertinaed inside each other. And so the D5s are all sitting on top of each other, and the D3s that were all sitting on top of each other turn into this layered structure where it's organized according to how many D3s and how many NS5s. And so there's a separation. And it sort of looks Coulomb branch, but it's still within the size.
Oh, it's not Coulomb branch.
Yes, let me finish. It's still within the same ADS3. So it's not Coulomb branch, but it looks a bit that way.
No, the Coulomb branch is on the left. Brains going through each other, not talking to each other. That's Coulomb branch. Brains on each other. That's Higgs branch.
Joseph, okay. I'm just trying to paint a picture here, which is normally when we think of brains separating, we think of, okay, Coulomb or Higgs branch. And yet they're separating within the same ADS3, which I think is really strange.
Yeah.
That feature could completely disappear when you go to compact Riemann surfaces. I don't know. But if I had to pass a measure, say, look for this in the conformal field theory, this might be a very general feature that we should look for.
Okay, I think also it's really a symbol of the field theory flowing in infrared to really a conformal field theory, and to in particular to good gauge theories, because it's really what's making you the label of the strength of the spike, because if each of them are self-similar, and if you had some bad or ugly gauge theories, what would happen is that
I can draw here.
You would have something like that, and you would have a second one which basically cross something like that. And basically, and if you have that, it means that it does not flow to an SCFT, and it has to recombine things and to go to do some
So putting it another way, the conformal fixed point field theory is defined by some partition, and there are good partitions and bad partitions. And these good partitions are exactly the precise steepness arrangements of the spikes. So there is something being encoded in the concertina of spikes that somehow represents some interesting feature of the infrared conformal fixed point. How that turns up in the kind of thing you're talking about, Matt, I don't know. I worry that it'll go away when you go to compact Riemann surfaces, but I'm not sure.
So I suspect if you want compact, you have to dissolve some of these branes. That was the only way one could get a compact S1, or the M theory version of what I was just talking about was the, something like T2. I think you have to dissolve one of the brane charges. But so maybe you're supposed to dissolve the spike here, or I think you said maybe even mention that, but I didn't quite follow.
This is in type 2B, you can get a compact Riemann surface, and you can get a compact CFT by just having these things. Maybe you can show them, Raphael. Maybe by just having these Riemann surfaces which have two ends. So you can take this Riemann surface which has an end here, that's compact, and another one. It's an infinite Riemann surface, but the metric caps off, and then you compute the central charge, and you have a very beautiful ADS4 times some space, and you can actually find the free energy, and you can do everything. So you have a clean CFT dual to ADS4. We don't have this construction for ADS3.
Okay.
Let me add a caveat, a word of warning. The way you set this up in supergravity is you have a non-compact infinite strip.
Yes.
Which the warp factors then compactify for you. Yeah. So it's not
okay. I see.
In your language, it's compact or non-compact. Back reaction collapses it. to a compact space. So, the thing I find compelling about the fact that it should be part of this is that in this context, the D3, NS5, D5 setting, the data, which is the steepness of the spikes, is critical parts of data of the conformal filter in the infrared limit. So I suspect that if there's an analog statement for the ADS3 times S3 times S3 times sigma, I would hope that there's going to be a similar story. The steepness of the spikes and the separation of the brains in the ADS3 limit might still be a feature, but I don't know.
Yeah.
And somehow, if you look at the brains again, there's this picture that you have some brains, and then they are basically there's some D5s, and then you have on the other hand some NS5s, and some D3s in between them. The CFT doesn't live on the intersection. The CFT lives actually here. The CFT lives actually on this corner, away from the intersection. That's where you get the CFT. So the flow, it's not you're not. So even if you put your intersecting brains on top of each other and you say, I'll do my intersecting brains and I'll get I'll get my CFT. It's actually the CFT doesn't live where the brains are. The CFT lives on the side of this brain. So that's why I think it's so hard to find the CFT by just saying, I have some brains on top of each other and they intersect, and I'm looking at the lower energy degrees of freedom. The lower energy degrees of freedom live here, but the CFT lives here. It's really a different location.
There's a somewhat intuitive reason why the CFT does that. If you've got a large number of NS5s and D5s, the number of D3s is the product of the number of NS5s and D5s. And so the whole thing gets overpowered by the D3s in the middle, and the center of this thing collapses into a scaling limit, pulling the NS5s and D5s into these spiked structures. So that the picture disappears, and you get these nice scaling, bending brains, which layer inside the ADS3. And I do wonder whether that could be somehow related to what we're talking about, the temperature dependence of the index, the fact that there's still a scale in your index calculation, which is
there is, yeah. So I think some very basic thing that I missed about this setup is how many supercharges can I preserve in the vacuum of this ADS4? Are these 1/8 BPS just because it's 3 sets of brains?
No, it's 2 sets of brains actually, naively, because one of them doesn't break any more supersymmetry. So
I see. Okay, it's one of those accidental. Yeah, it's similar with this D. Yes. Okay. I see. Because for me, the temperature dependence that showed up for me, the extra scale in the problem, was a feature of the large n equals 4 SUSY. Like, I mean, it's a consequence of representation theory when you have this really big supergroup. If you're breaking more supersymmetry than the large n equals 4, then I have no explanation that would work. But of course, all these things are very similar brain setups in string theory. That's one takeaway, is that the microscopic picture is kind of similar between these different proposals, and so maybe there's a more stringy reason that isn't tied just to a pure symmetry argument, because the symmetries wouldn't be the same in these setups. That's the SUSYs would be different here, right? So
in every case, you have the same large superalgebra, like the D1, comma gamma or comma alpha in your things. You exactly have the same superalgebra. So
this really is the same algebra.
Yeah, in M theory. Here
in theory,
a bit more.
Okay. I see. So that's.
But it's sort of clear where it's coming from, right? In your picture, it was coming from the ratio between the D5 and the D5 prime, which has to basically the size of the two S3 had to compensate the size of the ADS3.
Yes, exactly. That was the
same thing. Like, okay, you have the size of the two S2s, which has to compensate the size of the ADS4. And
okay. Yes.
So okay, that's kind of similar in this sense, I would say.
Yes, I agree with that. And the way that the supersymmetry at least for me, when you check Susie, even though you're adding several sets of branes, there's kind of a conspiracy of the projectors.
Yes.
Projection conditions. Is this the same
Yeah.
conspiracy? Okay. Wonderful, wonderful. Thank you. Yeah.
There's always given two projectors, there's always a third guy, which is the product of the projectors, which is a friend.
And that's the Hanani-Witten friend. So it's the friend which you get by crossing the branes through each other and getting Hanani-Witten. So
okay, that's wonderful. Thank you. Yes. Perfect.
So
yes.
But somehow, so I think the one thing which may be interesting, again, if we are to go hunting after the theory dual to this ADS 3 times S3, even in type 2B in your setup, I think one should try to build these spiky branes, because again, there's a Lunin system there, and there are some spiky branes which are sourcing your ADS. But again, I think your ADS is going to come from this region of the spiky branes. It will not come again from the branes intersection, from the brain intersection. It will come from the side, region. So maybe then one can read off the field theory, some way to couple field theory much better.
Maybe just because there's been several discussions about my talk here at the end of Raphael's. I should point out that Edward's proposal, just so that there's something to go off of, right? Edward has a proposal, and this is that it's some instanton moduli space with extra B flux. So his proposal for the dual CFT is a nonlinear sigma model whose target space is the moduli space of instantons on S1 cross S3 with an additional B field turned on. And so the charges work out so that their UN instantons is the number of 5 branes, and then there's the instanton number is the number of 1 branes, and then the units of B flux is the number of 5 prime branes. So in this setup here, is there a similar, if you try to think about the dual CFT in Raphael's setup, is there some way of matching the 3 discrete parameters, the rank of the gauge group, let's say the instanton number, and then the number of units of flux? Is there a similar dictionary?
In this language, there is a full dictionary, but it's really about 3D and equal parity CFTs, which are like some quiver gauge theories. So basically, you don't have only one gauge group. You have a bunch of gauge groups and some hypermultiplets on each of the gauge groups. And so the story is, let's say, a bit more.
But I think it's the same story, because there's a brane charge induced. So this N5 N5 prime over 2. This is induced from the B field. So you have the B field of the red brane, which goes on the blue brane and induces this instanton number.
And the Chern-Simons couplings,
which are these guys, which are free instantons. So you basically have 2 contributions from, if you think about the D1s and instantons inside D5s, then essentially this story is saying that the D5s are not clean, because again, there's a D5 prime which comes in and sources an instanton charge on your brain.
Yes,
so
yes.
I think
it is. Yes.
And that's what you just said to the N2, M5, M5 prime story. It's very similar to the D5, D5 prime, D1 story.
F1 story, actually.
No, I don't put it, you can teach your life. So basically, if I think about the M2, M5, M5 prime, then the M2, from the perspective of the M5, is basically a point inside an R4 of the M5. So that sounds a lot like our instanton moduli space.
Yes.
So and similarly, it's symmetric with respect to the other brane, the other M5 primed. It's also, the M2 is a point in that as well, and that's how that's suspended between. So, but if I focus on the first M2 and the first M5, that looks like an instanton moduli space. And when you put the M2 with the M5, the combined fluxes through the Chern-Simons interaction creates the flux of the third guy. So there is a context in which the third guy, the M5 primed, emerges as a dielectric flux sourced by the 2 primary guys. So that picture you just painted sounded rather similar.
Yes. But as long as there are really 3 independent parameters, right? Which there is here in this slide, right? The numbers of these branes are 3 independent controllable parameters.
Yes.
Whereas the induced flux, I would have thought that the number of units of induced flux.
So do you have a bound on one of the number which has to be bound by the product of the other? For example, like the number of disturbances here is less than the product of the number of NS5 times the number of D5. So for example, if you have this kind of relations, or do you have such a thing, or?
No, because I think this system corresponds to a D5, D5, F1 in type 2B. And then on top of that, you can come with the D5, D5, you can put D1s on as well. So I think the Witten calculation is actually adding, so you know, this guy, if you smear it, you can kill the F1s at all, so you kill the black guys, but you still have the bumpiness. And then you come with D1s on top. You are basically putting D1s on top. So I think, right, Matt, I mean, you know, this is, so the system we have right now here is basically 8 supercharges. The brains have 8 supercharges, and then, you know, when you zoom in the conformal stuff, you get 16.
Yes.
The system you have are actually D5, D5 prime, D1. So the brains there have 4 supercharges, and then you come with a D1 and you get 8. Is that so? Which so
the large n equals 4 preserves the same same number of supersymmetries as small n equals 4. So there's 16 supercharges total, right?
No, yeah, 8 and
that's
8.
n equals 4 supersymmetry in 2D, right? 2D n equals 4 is 16.
Supercharges and like the superconformal.
I'm just confused how the D1 comes in there, because I mean
that's where where you have the 16. You have 8 from the intersection of brains, and then because it's 8 years, and you have
you get 8 from the brain intersection. 8 from
yes.
Yeah, okay, yeah.
16 conformal plus Poincare charges. Yes.
Right. The D5 prime is not supposed to have the same killing spinners. So normally when you have a D5 and a D1, there's a friendly guy, which is basically an NS5. Unless, okay, we need to look a bit at the type 2B embeddings, because, you know, I think there's, I mean.
It's fine. Okay, I have the answer. Because for D5 and NS5, the number of common direction is 2 plus 1, right? So you basically have 3 in here and 3 in here. But for D5 and D5 prime, you have 4 and 4. So 4 and 4 is 8, and 8 are like the right number to have like a D5 and D5 prime. So it's really 8 supercharges, and it's on the nose the same thing. And that's why you have D1s, right? Because it's not the same. Here, like the NS5 and the D5 are, yeah.
I think I know. Can I stop for a second? I think the red guys, I mean, again, if you plot this Hanani-Witten story, I think the red guys in this case would be D5s, and the blue guys would be D1s, and then the black guys would be the D5 primes. The Hanani-Witten game is you have 3 brains which play the Hanani-Witten game with each other.
They all play together, right?
They all play together, but yeah. I think the way Matt gets the brains is actually going to be. But okay, we need to work this out.
But the one set of D5s for me is the induced, or it's maybe not, the induced is not the right word, but it's one set of brains is really a flux. It's a dissolved flux of them. And so it sounds like it's a D1. It sounds like the red and blue for me is D5 and D1.
Yeah, exactly.
Very good. Yeah, that's exactly right.
Okay, that's what you were saying. Okay, yes. I think that sounds correct. Yes.
Okay. So this is an induced contribution, and this is some honest to goodness physical extra brains. So there are 2 contributions. You can have induced, so there's an induced guy, and then you can put the black guys in between or not. It's up to you. So the induced guy is always there, and then you can put the black guys in between to get different gauge theories. You get different.
So there's a sense, though, that the induced guy, there's much more flux of the induced guy because it's the product of the charges of the other 2. And that usually dominates the IR fixed point. So is there any sense in which the D5 prime in your story, if it's the induced guy, is dominating the infrared?
Well, I think no, because at the end of the day, after you dissolve all the fluxes and fully back react, the 2 brain charges are totally symmetric, right? The first S3 for me and the second S3, they are the same, except they have different radii in general. So before, even though from the brain construction, I think this is crucial for my talk and this talk as well, is that the brain construction, it treats these asymmetrically, but the back-reacted supergravity solution, they're treated symmetrically. That was a property of the ADS3 cross S3 cross S3 cross S1, and it's a miracle that Witten's conformal field theory, which treats them asymmetrically, is supposed to reproduce a supergravity solution where they are treated symmetrically, right? So the branes and the superconformal field theory, the d5, d5 prime are not on the same footing, but the back-reacted solution, they're on the same footing. And so when talking about whether something dominates the infrared or whatever, I mean, from the point of view of just the supergravity, these two numbers are just two arbitrary choices. None is more important than the other. It's just in the dual CFT, they look very different in their footing. And also in the brane system, yeah. So, yeah.
Kind of surprising that it's the D5 and D5, like it's the D5 prime which plays a special role and not the D1, because you have
Exactly.
Yeah. The 2-3 spheres are like nice free cycles to integrate some 3-brane chart, right?
Yeah.
So 5-brane chart. So
but D5 and D5 prime, if they're the blue and the blue guy, then the guy in between is an F1. You need to be a D1.
Sorry, why would it be an F1? Maybe I didn't.
When you have two D5s oriented like 0, 1, and then 2, 3, 4, 5, and 0, 1, 7, 8. When you cross them through each other, you create by Hanani-Witten an F1.
Okay, it's a fundamental. All right. That's just.
Now, of course, if you smear and just making everything uniform, you'll kill this Hanani-Witten. So you can always kill the Hanani-Witten field, but you don't need to. And in general, it will be there. So this will be an F1 on this guy.
Does that make a difference to physics? It must make a huge difference to physics.
Having the F1 or not?
Having F1 versus having a D1.
But the D1 is in a different place. So those are D5. So this is a D5 along 0, 1, and then 1, 2, 3, 4. 0, 1, and 2, 4, 5. 2, 3, 4, 5. There's another one that goes 0, 1, 5, 6, 7, 8.
Yep.
Which are, and they together they create a Hanani-Witten for an F1 along the direction 9.
Okay.
And math has a D1.
D1 is this way, and D5 is this way.
Sorry, which way? Sorry. So the D1 is.
So these branes have a common direction.
The D1 goes to orthogonal to both D5s.
0, 1. Then there's a 3, and then there's like a 2, 4.
The D5 direction is common with one of the D5s, or orthogonal to it, or with one. And how is the D5 D1 oriented relative to the D5s?
I think one way of doing this setup is that you write you have one D5, right? And then you take the transverse space and write it as T star of S3 or something like that, and then you just smear D5 flux over it. And that becomes one of the S3s. One of the S3s has a smeared D5 flux. If you do the perpendicular or orthogonal intersecting, it's going to be a picture like this. I mean, we can bring it up from it's not in my paper actually, because we didn't use the orthogonal D5s, right? For me, one of the D5s is induced.
Yeah.
For Raphaël.
Yeah.
No, but I think I understand what's going on. There's an F1. The F1 you have is an extra ingredient in this game. There's a D1, sorry.
D1.
The D1 you have would be along 0, 1, and you brought it down to type, and you reduce to type to be on. You reduce to go to type from M theory. You reduce down on 3.
What's that? So is that 7, 8, 9, 10?
7, 8, 9, 10, yes.
Yeah.
Okay.
So I'm in M theory. I have some M5s.
So wait a minute.
Yeah.
If your D5s don't have, are they 0, 1, or where are they going?
So the M5s are, I put them with blue. So one D5.
I want to know they've only got 4 spatial directions on your D5. Where are they?
5. Everybody is along 1.
Everybody's along 1.
Yeah. So in M theory, you have an M5 on 0, 1, 2, 3, 4, 5, and then there's an M5 on 0, 1, 7, 8, 9, 10. And there's a direction which is 1, which is 3, sorry, where you have so the direction 3 is the one here. This is the direction 3.
Yep.
I'm smearing on 3, and I'm reducing the whole thing down on 1, on 3, down to type 2A. And if I S-dualize, I get what you have.
Yeah.
But the direction is, and then I'm on top of that, I'm coming with a D1, and I'm putting a D1 along 0, 1. on top of these things.
If you're going to go down on the 3, that will give you D4s, won't it?
No. It will give me NS5.
NS5, yeah.
NS5.
Yeah. Then you have to do S duality, but then
That's what I think.
Oh, good, very good.
But then there's a D1 on 0. Oh yeah, there's a D1. There's an F1 on 0. No, sorry. The M2 I had, which is my.
It comes an
Yes.
F1. When you
It comes an
S,
F1.
everybody comes Ds. It's
Yeah.
It's the S children what we know.
Yeah, that's all of what you have.
Yeah.
Okay.
yes, yes. If you want to go from M theory, you would do the reducing on 3.
Or in type 2A, you need first to do duality and then to S dualize. Yeah, I mean, you are in type 2A if you reduce.
I have an F1 and S5 in type 2A.
Yeah, you
That's what you want.
No, you dualize once, you are in type 2B, and then you S dualize and you are.
Yes, indeed.
So
Which ones?
But you don't mess anything up.
Yeah,
right?
no.
Okay.
Very good.
But I don't see this Hanani and somehow this Hanani and yeah, but you're right at the supergravity level, it's all
You just
democratic.
have to write down the projection
Yeah.
theory and see what happens. And you'll
Yeah.
exactly.
Okay.
There's not much difference in a D1, D1.
No, it's the same bloody system, so you know. But again, I think the point is that somehow the physics here is given by the spikes, which are not, I mean, even in type 2A, when you reduce on this direction, even if you smear these guys, you still have some spikiness in type 2A. You should see some spikiness in type 2A. It's hard to see at the level of the solution, but for example, you can put brane probe spikes in this ADS3 times S3 times S1. I'm sure you can put some brane probe spikes which have a D5, D1 spike. Yeah, you can put some brane probe spikes in this background.
There are not many non-compact directions once you're already in the ADS3 region, right? I mean, you can't have a spike that goes out forever because everything is compact. Except for I mean, even the ADS in global coordinates is compact.
It's a spike which is fully along the Poincare ADS.
Poincare ADS.
Yeah, okay. In Poincare, yes, yeah.
That's always, we always use the Poincare ADS because that's really the one which are that spike state.
Right.
Scaling and yeah.
Right. Okay.
Anyway, that was very useful.
Yes, thank you.
Our brains. More questions for Raphaël?
No, if I had to bet, there has to be some connection between the spike decomposition and your long character decomposition.
Yep.
The index. It's just,
well, to be clear, the characters that appear in my story were written down in like the 80s before the like anomaly cancellation happened. So the characters are representation theory objects. Giving them a brain interpretation, though, that part I wouldn't know, but it's possible. But they're usual SU2 characters for me. Nothing fancy, right? They're just labeling all the spins on the S3.
It's the beta dependence that I just can't get my head around. Okay.
We'll figure it out.
Yeah, the beta dependence for me was very new. It's obviously that there's an extra scale in the problem, even though you've preserved supersymmetry, it's like you can't. Scaling the radius is not a Q exact deformation because the Q acts non-linearly. Is there any? I guess I don't know. My only explanation relies on the large n equals 4 supersymmetry. I don't know an example in let's say 3D n equals 4 superconformal field theories or 3D n equals 6 or something like that, right? And like I don't have an explanation for how you could get temperature dependence in those theories. Like the mechanism for me relies on the large SUSY. So yeah.
Okay.
Maybe can I ask you a question? So if I started with, let's say I had M theory on ADS3 cross S3 cross S3 cross sigma G, and sigma G is a compact Riemann surface.
Yes, we don't have that yet, but it's coming.
Okay. That because that is the case where then if you had with the compact Riemann surface case, which is similar to the strip picture, but then I quotient with gamma, or is it more like the rather than a strip with two boundaries, it's the upper half plane mod gamma. But either way, okay. So let's say that you have the Riemann surface compactification, right? If the Riemann surface is not T2, in general, I'll break SUSY entirely, right? So the Riemann surface has to be fibered in some way.
No. In M theory, you have the same supersymmetry. For any Riemann surface you want, you get the same supersymmetry.
But it's not maximal, right? I mean, or not, well, obviously it's not maximal, but the T2 will preserve more than a genus G surface, correct? Or
no.
The Doka paper classifies everything, and the T2 is a degenerate limit. So he classifies everything with basically 8 supersymmetries.
Yes.
In that paper, T2 emerges as a degenerate limit. Now, it's possible there's some enhancement. I doubt it somehow. I think it's
there's no enhancement.
It's generally 8 supersymmetries, and the underlying brain structure says there can't be any more than 8 supersymmetries.
Eight Poincare supercharges before we get the conformal ones, right?
Yeah, Poincare.
Yeah.
So
Right.
The brain structure.
For any Riemann surface, that's true. So that means that there should be again, taking some T dualities and swapping out the brains. Does that imply that there should be like a large, infinite family of 2D theories that have the large n equals 4 supersymmetry by uplifting?
If we can do this, so clearly people have done a large number of 3D theories.
Yes.
These, which are all these quiver gauges, and they're classified by basically Young tableaus breaking up into two sides and so on.
Yes.
So I'm sure there'll be a similar story in M theory. We just don't have it yet, and we didn't. I mean, until this morning, we didn't think that we should get it. I mean, I think if we look a bit into it, we'll get it. But
let me add the word of warning. So Doka's calculation involves breaking the system down to, first of all, you pick your Riemann surface, some harmonic function on the upper half plane. Having harmonic function, you have to solve, albeit it's a nice one, a linear differential equation, but the differential equation on that Riemann surface, but then there's a whole mess of regularity conditions you have to satisfy, which might cause all sorts of problems and exclude all sorts of solutions. So there are very few examples that are known, except for the upper half plane itself, where it's a systematic classification.
Right.
Start compactifying the Riemann surface. There is, the paper's full of these consistency conditions and smoothness conditions, and a lot of the times they break down, particularly when you start modding out by discrete groups, because discrete groups have fixed points and fixed surfaces, which can cause all hell to break loose with the differential equation you solve. So I don't have enough intuition with the system of equations he's got to say there's a vast number of them. It could equally well be that there's very few of them.
I see. But it's nice to have more than one example,
Well, the upper half plane, there's lots of examples. It's a very,
but they're not compact.
But they're not compact.
I would hope to have at the end, a CFT with a compact target space, right?
Exactly. You've inspired us to think more carefully about compact Riemann surfaces and nothing else.
Yeah, because even if there are a lot of constraints, if you can find a family of examples, because right now Ed's paper is the only one that makes any proposal in the 30-year history of the subject. So if there's a big family of M theory examples I can build starting from the general Riemann surface, that's already very interesting, independent of the whatever super black hole microstate counting or stuff like that. Although I might argue that if it preserves large n equals 4 in some sense, then something about what I said would apply in this system for a general Riemann surface. But that would be very interesting to. I would look at look at the intro of Ed's paper to fact check some of the things I've said here about the brain construction, because he gives a nice overview of how his conformal field theory guess is motivated by some particular intersecting brain construction, not too dissimilar from this that we're talking about, but not exactly the same.
My brain is full.
Okay. Yeah. Thanks a lot. Sounds good. Thanks a lot. Thanks a lot, everybody. Again.
Yeah, thank you.
Conference. Thanks for all the input. It was really great. It was really great having everybody here, and thanks to those who came to Saclay, and hopefully we'll see each other next year.
Hopefully we'll cross paths soon.
Cross paths before. Okay.
Bye.
Bye.
And let's have a big thank you for the organizers, Joseph Neves.
Not too much to organize on Zoom. Just send an email to people telling me, give a talk next week, Monday, 5 o'clock, Okay, thanks. Bye, guys.
Bye.